The Milky Way is an enormous home in space, filled with billions of stars and trillions of planets. Around them float huge clouds of dust and streams of blazing hot gas. Together, they create the amazing system we call a galaxy. How wide is our galaxy, and what does that size mean for everything within it, including us? Before we begin, drop it in the comments section below where in the world you're watching from and what time it is there now. Now settle in as we try to grasp the true size of the entire Milky Way galaxy. You probably already know a little about our solar system. At the very least, you might know that it contains 8 planets, including Earth, which all orbit the Sun. Along with the planets, there are also many moons, countless asteroids, and even dwarf planets such as Pluto. But what lies beyond the solar system is far more vast and mysterious than most people realize. From Earth, without any telescope, the human eye can see about 6,000 stars scattered across the night sky. That might sound like an enormous number, but in truth it represents only the tiniest fraction of what is really out there. For every single star you can see, there are more than 20 million you cannot. The majority of stars are either too far away, too faint, or hidden behind huge clouds of cosmic dust. All of these visible and invisible stars belong to our own galaxy, the Milky Way. Yet the Milky Way is only one galaxy among many. For example, the nearby Andromeda galaxy is even larger than ours. Every galaxy is a huge system containing billions of stars, their planetary systems, stellar remnants such as white dwarfs and black holes, as well as interstellar gas and dust. Astronomers now estimate that there are around 100 billion galaxies in the entire universe, but even that number is uncertain because our instruments cannot yet detect them all. Between these galaxies stretches what is called intergalactic space, a vast region filled with only a very thin spread of gas. When you think about how big even our own solar system is, and then realize it is just one among countless others inside a single galaxy, it becomes easier to understand why many scientists describe the universe as effectively infinite. This perspective highlights just how small Earth, and humanity itself, truly is within the wider cosmos. Over the past 100 years, scientists have learned much about the material that fills the spaces between the stars, known as the interstellar medium. Using powerful radio telescopes and X-ray telescopes, they discovered that this medium is made mostly of thin, ionized hydrogen gas, dust particles, and energetic cosmic rays. Within thick interstellar gas clouds, new stars are often born. Yet even just beyond the edge of our own solar system, there is still much that remains unknown. This region includes the Kuiper belt, a vast ring of icy bodies and debris located between 30 and 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun. Surrounding all of this is the heliosphere, a gigantic bubble created by the solar wind, streams of charged particles constantly released from the Sun. This bubble acts like a protective shield, blocking most harmful cosmic rays and high-energy particles from reaching the planets. Without the heliosphere, life on Earth may have developed very differently, or perhaps not at all. The outer boundary of the heliosphere, where the Sun's magnetic bubble finally gives way to true interstellar space, is called the interstellar boundary. Inside this bubble, the solar wind carries plasma, or ionized gas, outward. But eventually the wind slows down as it collides with the pressure of the interstellar medium. This slowdown first occurs at a region known as the termination shock, where the solar wind, once travelling at speeds between 370 and 430 miles per hour, suddenly drops to around 62 miles per hour. Beyond this lies the heliosheath, an area where the solar wind continues to slow and interact with interstellar plasma. Finally, at the very edge, lies the heliopause. This marks the true outer boundary of the heliosphere, around 11 billion miles, or 18 billion kilometers, from the Sun. Beyond the heliopause begins interstellar space. Since the start of space exploration, only 2 human-made probes have crossed into this region beyond our solar system. Voyager 1, launched in the year 1977, was the first. It took more than 30 years for the spacecraft to reach the heliopause, the border of interstellar space. Once it passed through, Voyager 1 continued its journey, sending back priceless information from a realm no longer influenced by the Sun's magnetic bubble. it remains one of humanity's greatest scientific achievements. After the discovery of Pluto in the year 1930, astronomers quickly began to wonder if this small and distant world might not be the only body of its kind. For decades, scientists put forward different theories about a region beyond Neptune, where many more frozen objects might exist. This region would eventually come to be known as the Kuiper Belt. But it was not until the year 1992, more than 60 years after Pluto was first spotted, that clear and direct evidence finally confirmed its existence. Because so many different scientists had speculated about such a region in different ways, there is still debate today about who should be credited with being the very first to propose the idea. The earliest astronomer to raise the possibility of a population of objects beyond Neptune was Frederick C. Leonard. Soon after Pluto's discovery by Clyde Tombaugh in 1930, Leonard asked whether Pluto could actually be the first of a series of ultra-Neptunian bodies, suggesting that many more still remained hidden, waiting to be found. That same year, another astronomer, Armin O. Leuschner, proposed that Pluto might only be one of many long-period planetary objects yet to be discovered. In the year 1943, Kenneth Edgeworth published a paper in the Journal of the British Astronomical Association. He argued that, in the far-off region beyond Neptune, the material left over from the birth of the solar system had been too spread out to gather into full-size planets. Instead, he suggested that material condensed into countless smaller worlds. From this, he concluded that the outermost parts of the solar system must be filled with a vast number of small objects, and that, every once in a while, one of them might wander inward, becoming visible to us as a comet. In the year 1951, Gerard Kuiper published a paper in Astrophysics, a topical symposium, where he discussed the idea of a disk-like structure that had formed in the earliest days of the solar system. He thought this disk was made up of leftover icy fragments, which had broken apart over time, much like star clusters that eventually dissolve. In another paper, based on a lecture he gave in 1950 titled On the Origin of the Solar System, Kuiper described an outermost region of the solar nebula, stretching from 38 to 50 astronomical units away from the Sun. In this zone, he believed ices of water, ammonia and methane clumped together into objects as large as 1 kilometre or more. According to him, these clumps could account for comets in terms of size, composition and number. Kuiper also argued that Pluto, then thought to be as large as Earth, was sweeping through this entire region, scattering many of these bodies across the solar system. If his assumption about Pluto's size had been correct, then the Kuiper Belt as we know it would not exist today. Other scientists continued to expand on the idea in the following decades. In 1962, physicist Alistair G.W. Cameron suggested that the edge of the solar system might hold a tremendous mass of small material. In 1964, Fred Whipple, the astronomer famous for his dirty snowball model of comets, proposed that a comet belt could even be massive enough to explain the unusual movement of Uranus, which had led astronomers to search for a so-called Planet X. His idea was later disproven by observations, but it kept the debate alive. In 1977, Charles Cowell discovered the icy body later named 2060 Chiron, which orbits between Saturn and Uranus. He used the same type of instrument, a blink comparator, that Clyde Tombaugh had once used to discover Pluto nearly 50 years earlier. In 1992, another similar object, later called 5145 Pholus, was discovered. Today, we know of an entire group of such comet-like bodies, called the Centaurs, which orbit between Jupiter and Neptune. These orbits are unstable, lasting only a few million years, so scientists concluded that they must be replenished from a larger reservoir farther out in the solar system. Additional evidence for the Kuiper Belt came from studying comets. Astronomers had long known that comets could not last forever. Each time a comet approaches the Sun, the heat causes its icy surface to vaporize, gradually eroding it. Since comets still appear regularly in our skies, there must be some region in space that continually replenishes them. One possible source is the Oort cloud, an enormous spherical swarm of icy objects proposed in the year 1950 by Dutch astronomer Jan Oort. The Oort cloud may extend out to 50,000 astronomical units from the Sun and is believed to be the origin of long-period comets, those with orbits lasting thousands of years, such as the famous Hale-Bopp comet. There is another group of comets known as short-period comets, or periodic comets. These are the comets that return relatively quickly, making a full trip around the Sun in less than 200 years. A famous example is Halley's Comet, which reappears in the night sky roughly every 76 years. By the 1970s, astronomers noticed something puzzling. The number of short-period comets being discovered did not match the idea that they were all coming only from the distant Oort cloud. For a comet to travel from the Oort cloud into the inner solar system and then become a short-period comet, it would first have to be captured by the gravity of the giant planets. This process seemed far too inefficient to explain the large number of short-period comets actually observed. In the year 1980, Uruguayan astronomer Julio Fernandez published a paper in the monthly notices of the Royal Astronomical Society. In his calculations, he showed that for every short-period comet that managed to enter the inner solar system from the Oort cloud, about 600 others would be lost forever, flung out into interstellar space. To solve this mystery, Fernandez suggested that there must be another source much closer to the Sun, a belt of comets located between 35 and 50 astronomical units from the Sun. A few years later, in 1988, 3 Canadian astronomers, Martin Duncan, Tom Quinn and Scott Tremaine, tested this idea by running computer simulations. They wanted to see if all the observed comets could truly have come only from the Oort cloud. Their results confirmed Fernandez's suspicion. The Oort cloud alone could not explain the observed patterns. Short-period comets tended to be concentrated near the plane of the solar system, while Oort cloud comets could arrive from almost any direction in the sky. When they included a belt, as Fernandez had described, the simulations finally matched reality. Reportedly, because the words Kuiper and comet belt appeared in the opening line of Fernandez's paper, Tremaine decided to name this hypothetical region the Kuiper belt. Meanwhile, in 1987, astronomer David Jewitt, who was then working at the Massachusetts Institute of Technology, MIT, grew increasingly intrigued by what he described as the apparent emptiness of the outer solar system. He believed there had to be more beyond Pluto. Jewitt encouraged his graduate student Jane Liu to help him search for objects past Pluto's orbit, telling her, "If we don't do it, nobody will." Using telescopes at the Kitt Peak National Observatory in Arizona and at the Cerro Tololo Inter-American Observatory in Chile, they began their search. Their method was very similar to the one Clyde Tombaugh used to discover Pluto in the year 1930, comparing photographic plates with a device called a blink comparator. At first, checking each pair of plates took around 8 hours, but their work became much faster with the arrival of electronic charge-coupled devices, or CCDs. Although early CCDs could only capture a small area of the sky at a time, they were far more sensitive than photographic plates. A CCD could keep about 90% of the light that reached it, while traditional photographs kept only about 10%. Another advantage was that the blinking process could now be done directly on a computer screen instead of by hand. Today, nearly all astronomical observations rely on CCDs. In 1988, Jewitt moved to the Institute of Astronomy at the University of Hawaii. Liu later joined him, and together they used the University of Hawaii's 2.24-meter telescope on Mauna Kea. As CCD technology improved, detectors grew to cover areas of 1024 by 1024 pixels, making searches much more efficient. After 5 long years of careful searching, on the 30th of August, 1992, Jewitt and Liu finally announced their discovery, the first confirmed object in the Kuiper belt, which was given the temporary name 1992 QB1. This object was later officially named Albion and catalogued as number 15,760. Just 6 months later, they found a second object, later catalogued as 181,708 1993 FW. From that point onward, discoveries came rapidly. By the year 2018, astronomers had identified more than 2,000 Kuiper belt objects. In the first 2 decades alone, from 1992 to 2012, over 1,000 bodies were found in the region, showing that the solar system's outer belt is filled with icy objects beyond Pluto and Albion. Even in the 2010s, however, scientists still did not fully understand the extent and nature of Kuiper belt bodies. The first close-up studies had to wait for spacecraft. In the year 2015, NASA's New Horizons mission flew past Pluto and its moons. giving humanity its first detailed look at the Plutonian system. Then, in the year 2019, the same spacecraft visited another Kuiper Belt object, Arrokoth. Later studies revealed an even more complex story. Astronomers now know that the Kuiper Belt itself is not the birthplace of short-period comets. Instead, these comets mostly come from a related region called the scattered disk. The scattered disk was formed long ago, when Neptune drifted outward from the Sun. In doing so, it reshaped the early Kuiper Belt. Part of the population was left behind in stable orbits, forming the Kuiper Belt as we know it, while another part was left in unstable positions where Neptune's gravity could still disturb them. These unstable objects became the scattered disk, and it is now thought to be the true source of most periodic comets. Different names are sometimes used for this region. Some call it the Edgeworth Kuiper Belt to include the Irish astronomer Kenneth Edgeworth, though others argue that neither Edgeworth nor Gerard Kuiper described anything like what we see today. Astronomer Fred Whipple, in fact, came closer to the modern idea. David Jewett himself has said that Fernandez deserves the most credit for predicting the Kuiper Belt. Kuiper Belt objects, or KBOs, are sometimes called Kuiperoids, a name suggested by Pluto's discoverer Clyde Tombaugh. In modern astronomy, however, the more neutral term trans-Neptunian object, TNO, is preferred, since it refers broadly to any object orbiting the Sun beyond Neptune, not just those in the Kuiper Belt. At its largest reach, if we include its farthest parts but leave out the scattered disk, the Kuiper Belt stretches across a distance from about 30 astronomical units to about 55 astronomical units away from the Sun. The main section of the belt is usually described as lying between two special points, known as orbital resonances with Neptune. The inner boundary is the so-called 2 to 3 resonance at roughly 39.5 astronomical units, while the outer boundary is the 1 to 2 resonance at around 48 astronomical units. The Kuiper Belt is not a thin, flat ring. Instead, it is surprisingly thick. Most of its objects can be found spread up to 10 degrees above and below the ecliptic, the plane in which the planets orbit, and some even farther, scattered in a wider cloud. Because of this, the belt is shaped more like a donut, or torus, rather than a narrow belt. On average, the belt itself is tilted by about 1.86 degrees from the ecliptic. Neptune plays a key role in shaping the Kuiper Belt. Its strong gravity, over the course of billions of years, the age of the solar system, can destabilize the orbits of objects in certain regions. These objects may then be forced inward toward the planets, outward into the scattered disk, or even completely out of the solar system into interstellar space. This influence creates clear gaps in the distribution of Kuiper Belt objects, much like the Kirkwood gap seen in the asteroid belt. For example, in the area between 40 and 42 astronomical units, no object can remain stable for long, and so anything found there today must have arrived fairly recently. Between the 2 to 3 and the 1 to 2 resonances with Neptune, roughly 42 to 48 astronomical units, objects are able to remain in their orbits for very long times without being disturbed. This region is called the classical Kuiper Belt, and it contains about 2/3 of all the Kuiper Belt objects, KBOs, discovered so far. The very first modern KBO ever found in the year 1992, originally named 1992 QB1 but later given the name Albion, belongs to this group. Because of this, classical objects are often called Kubewanos, a nickname based on the letters and numbers of Albion's original designation. The International Astronomical Union has set rules stating that classical KBOs must be named after mythological beings linked to creation. The classical Kuiper Belt is actually made up of two different kinds of populations. The first, called the dynamically cold group, travels in paths that look very much like the planet's orbits, almost circular, with eccentricities less than 0.1 and staying close to the plane of the solar system, tilted by no more than 10 degrees. Within this cold group is a denser concentration of objects called the kernel, located at semi-major axes between 44 and 44.5 astronomical units. The second group, called the dynamically hot population, has orbits tilted much more steeply, sometimes by as much as 30 degrees. The terms hot and cold here do not refer to temperature, but instead are borrowed from the behaviour of particles in a gas. The hotter they are, the faster and more chaotic their motions become. The two groups differ in more ways than just their orbits. The cold objects tend to appear redder and brighter, have a higher number of binary systems, and lack very large bodies. They also have a different size distribution compared with the hot group. Interestingly, the total mass of the cold population is about 30 times smaller than that of the hot population. Scientists think that these differences in colour and brightness reflect differences in composition, suggesting that the two groups formed in different places. The hot population is believed to have formed closer to Neptune's original orbit and was scattered outward during the giant planet's migration. The cold population, on the other hand, seems to have formed in its present location, since fragile binary systems would not likely survive repeated encounters with Neptune. Some scientists suggest that the difference in colours may also be due to different surface evolutions over time. Another important feature of the Kuiper belt involves orbital resonances with Neptune. If an object's orbit matches a simple ratio with Neptune's orbit, it can be locked in a synchronized rhythm, allowing it to remain stable. For example, in the 2-to-3 resonance, an object circles the Sun twice for every 3 orbits of Neptune. Pluto is the most famous member of this group, along with about 200 other known objects. These are called Plutinos. Although Plutino's orbits cross Neptune's, their resonance ensures that they never actually collide. Plutinos usually have very stretched orbits, showing that they were likely thrown into place by Neptune's migration. According to International Astronomical Union rules, all Plutinos must be named after deities of the underworld, following Pluto's example. Farther out, the 1-to-2 resonance is found at about 47.7 astronomical units. It is much less populated, and its members are sometimes called Tutinos. Other resonances exist as well, such as 3-to-4, 3-to-5, 4-to-7, and 2-to-5. Neptune also has Trojan objects that share its orbit, sitting at gravitationally stable points ahead and behind the planet. These Trojans are locked in a 1-to-1 resonance with Neptune, and often have long-lasting stable orbits. Curiously, there is a clear lack of objects with semi-major axes inside 39 astronomical units that cannot easily be explained by today's resonances. The leading idea is that when Neptune migrated outward in the distant past, its shifting gravitational resonances swept through this region, pushing out or capturing most of the bodies that once resided there. Astronomers studying the Kuiper belt have noticed something strange at its far edge. At a distance of about 48 astronomical units from the Sun lies what is called the 1-to-2 resonance with Neptune. Beyond this point, very few objects have been found, making it appear like the outer boundary of the classical Kuiper belt. However, scientists are still not certain if this really is the final edge, or if it simply marks the beginning of a broad, nearly empty gap. A few objects have been discovered much farther out, near the 2-to-5 resonance at roughly 55 astronomical units, well beyond the main classical belt. Predictions once suggested that large numbers of bodies should exist between these two resonances, but observations so far have not confirmed this. Early models of the Kuiper belt, based on the estimated mass needed to form planets such as Uranus and Neptune, and even bodies as large as Pluto, suggested that the number of large objects should actually increase beyond 50 astronomical units, possibly by as much as a factor of 2. Instead, astronomers found the opposite, a sudden and dramatic drop in the number of objects. This sharp decline is known as the Kuiper Cliff, and its cause remains a mystery to this day. In the year 2003, astronomers David Bernstein, David Trilling, and their team confirmed that this drop is real, and not simply the result of missing objects because of limited telescope observations. Several explanations have been suggested. Perhaps the material that far from the Sun was too thin or too spread out to clump together into large bodies, or maybe processes that happened later destroyed or scattered away those objects. Patrick Lekauka of Kobe University even proposed that the gravity of an undiscovered planet, perhaps similar in size to Earth or Mars, could be responsible. Recent studies of data from trans-Neptunian objects, up to September of the year 2023, show that the pattern of objects at the far edge of the classical belt looks similar to the outer main asteroid belt in the inner solar system. Both seem to contain mysterious gaps. In the Kuiper belt, a gap appears around 72 astronomical units from the Sun, far away from any known resonances with Neptune. In the asteroid belt, a similar gap is caused by Jupiter's 5-to-6 resonance at about 5.875 astronomical units. Despite decades of research, the exact origin and structure of the Kuiper belt remain uncertain. To solve these puzzles, astronomers rely on wide-field survey telescopes. One of the first, Pan-STARRS 1, finished its main science mission in the year 2014, and its full dataset was released in the year 2019. greatly expanding the number of known Kuiper Belt objects. Future surveys, especially with the Large Synoptic Survey Telescope LSST, are expected to discover thousands more objects and provide critical clues. The Kuiper Belt is believed to be made up of planetesimals, the leftover fragments from the original disk of dust and gas that surrounded the young Sun. These fragments never grew large enough to become full planets. The biggest of them, such as Pluto, are less than 3,000 kilometers across. Studies of the craters on Pluto and its moon Charon suggest that smaller Kuiper Belt bodies did not form by slowly sticking together from tiny kilometer-sized pieces. Instead, they likely formed directly as much larger objects tens of kilometers wide. Theories for how this happened include the gravitational collapse of clouds of small pebbles inside turbulent swirls of the early solar system's disk, or through processes known as streaming instabilities. In some cases, these collapsing clouds may have split into two, creating binary objects that orbit one another. Modern computer simulations show that the Kuiper Belt was heavily shaped by the giant planets, especially Jupiter and Neptune. In fact, Uranus and Neptune could not have formed where they are now because there was not enough material in that region. They probably formed closer to Jupiter and then migrated outward. As the early solar system evolved, the orbits of Saturn, Uranus and Neptune drifted outward, while Jupiter moved slightly inward. Eventually, Jupiter and Saturn reached a precise 1:2 resonance, meaning Jupiter orbited the Sun twice for every one orbit of Saturn. This powerful gravitational alignment destabilized the orbits of Uranus and Neptune, throwing them outward onto eccentric paths that disrupted the ancient planetesimal disk. When Neptune's orbit was still eccentric, its gravitational resonances overlapped, and planetesimals moved chaotically, spreading outward as far as Neptune's 1:2 resonance. Over time, as Neptune's orbit became more circular, it shifted outward toward its present location. During this migration, many planetesimals were trapped in resonances, while others escaped into stable orbits. Some were scattered inward and captured as Jupiter Trojans, irregular satellites of giant planets, or as outer asteroid belt members. Most, however, were flung outward and ejected entirely from the solar system. This process may have reduced the Kuiper Belt's original population by more than 99%. To explain these events, scientists developed what is called the Nice model, named after the city of Nice in France where it was first created. This model successfully explains many features of the Kuiper Belt, such as its cold and hot populations, its resonant objects, and the scattered disk. However, it still struggles with details. For example, it predicts slightly higher orbital eccentricities for classical Kuiper Belt objects than astronomers observe. It also cannot fully explain why so many binaries survive in the cold belt when they should have been disrupted by Neptune. Later versions of the Nice model suggest that the solar system originally contained not 4 but 5 giant planets, including an extra ice giant. Roughly 400 million years after the solar system's birth, this extra planet was thrown onto a path that crossed Jupiter's orbit and was eventually ejected into interstellar space. The surviving planets then continued migrating until the planetesimal disk was mostly cleared away. In these updated models, Neptune's outward journey explains the formation of the dynamically hot and cold populations of the Kuiper Belt. When Neptune migrated from 24 to 30 astronomical units over a span of about 30 million years, its movements captured some objects into resonances and scattered others into different orbits. The cold classical belt may have preserved its local population because Neptune's eccentricity stayed low, avoiding the chaotic scattering predicted by the original model. Even today, the Kuiper Belt remains a laboratory for understanding the earliest history of the solar system. Every new discovery of a distant icy world helps scientists piece together how the giant planets moved, how small bodies formed, and how our planetary system came to look the way it does now. Because the Kuiper Belt lies very far away from the Sun and from the larger planets, the objects found there are thought to be much less altered by the violent processes that changed most of the other bodies in the solar system. For this reason, finding out what these Kuiper Belt objects, or KBOs, are made of can give us important clues about the original ingredients of the solar system when it was first forming billions of years ago. However, studying them is very challenging. These objects are not only extremely small compared to planets, but they are also at an enormous distance from Earth. This makes their chemical composition very difficult to measure. astronomers usually rely on a technique called spectroscopy to determine what distant celestial bodies are made of. In spectroscopy, the light coming from an object is split into its component colours, producing something similar to a rainbow. This rainbow-like image is called a spectrum. Different materials absorb light at different wavelengths, and when astronomers examine the spectrum of an object, they see dark lines, called absorption lines, where specific substances have absorbed certain wavelengths of light. Since every element and compound has its own unique signature of lines, astronomers can identify the object's composition by studying this spectral fingerprint. Analyses have shown that Kuiper belt objects are mostly mixtures of rock and different kinds of ices. These include water ice, methane ice, and ammonia ice. Because the temperature in the Kuiper belt is only about 50 degrees above absolute zero, roughly minus 223 degrees Celsius, many substances that would normally be gases closer to the Sun remain frozen solid in this distant region. Still, scientists only know the detailed densities and proportions of rock and ice for a small number of KBOs, usually the larger ones for which both size and mass have been measured. Astronomers measure diameter in several ways, by taking detailed images with powerful telescopes such as the Hubble Space Telescope, by observing how long it takes for the object to pass in front of a distant star, an event called an occultation, or most commonly by estimating how much sunlight it reflects, its albedo, and comparing that with its heat emissions in the infrared. Masses can only be determined for objects that have moons orbiting them, because the movement of the moon provides the necessary gravitational data. As a result, densities are known for only a few binary systems. The densities range from less than 0.4 grams per cubic centimetre to about 2.6 grams per cubic centimetre. The least dense objects are thought to be mainly icy, with a lot of empty space within them, making them porous. The densest ones are believed to be mostly rock with just a thin outer crust of ice. In general, smaller Kuiper belt objects tend to have lower densities, while the largest ones have higher densities. A possible reason for this pattern is that collisions between objects may have stripped away some of the ice, leaving behind denser, rockier bodies. When astronomers first studied KBOs, they could not yet make out detailed information, so they focused on something simple: their colours. Early observations showed that KBOs range from neutral grey to deep red. This wide variety suggested that their surfaces were made of very different compounds, from dirty ice mixtures to hydrocarbon-rich substances. This finding was surprising because scientists had expected all KBOs to be uniformly dark, with much of their volatile ices lost over time due to cosmic rays. Different theories were suggested to explain the colour diversity, such as resurfacing caused by impacts or outgassing of materials. In the year 2001, astronomers David Jewett and Jane Liu studied the spectra of many Kuiper belt objects and discovered that the range of colours was too great to be explained simply by random impacts. Instead, they suggested that sunlight and radiation might chemically alter methane on the surfaces, producing complex organic compounds known as tholins, which give a reddish colour. The dwarf planet Makemake, for example, has been shown to contain several hydrocarbons that are products of radiation acting on methane, such as ethane, ethylene, and acetylene. Although most KBOs are still too faint to show strong spectral features, astronomers have had some successes. In the year 1996, Robert H. Brown and his team studied the KBO known as 1993 SC, and found that its surface composition closely resembles that of Pluto and Neptune's moon Triton, with large amounts of methane ice. Smaller KBOs, on the other hand, are often identified only by their colour and reflectivity. Many fall into two groups: grey objects with low reflectivity, low albedo, and very red objects with higher reflectivity. A possible explanation for this difference is the presence or absence of hydrogen sulfide on their surfaces. Objects far enough from the Sun retained hydrogen sulfide, which, when exposed to radiation, gave them a reddish colour. The largest Kuiper belt objects, such as Pluto and Quaoar, are different again. Their surfaces are rich in volatile compounds like methane, nitrogen, and carbon monoxide. Because these substances can occasionally evaporate in the frigid 30 to 50 Kelvin range of the Kuiper belt, and then fall back down as snow, they remain present on the surfaces of these larger bodies. Their ability to retain these volatile materials depends on both surface gravity and temperature. Water ice has been found on several objects, including members of the Haumea family such as 1996 to 66, mid-sized objects like 38,628 Huya and 20,000 Varuna, and even some much smaller bodies. In addition, crystalline water ice with a structured pattern, has been detected on larger and medium-sized KBOs, including 50,000 Quaoar, where ammonia hydrate has also been discovered. This combination of crystalline ice and ammonia suggests that some of these objects may have experienced internal activity in the past, with ammonia lowering the melting point of water and allowing limited tectonic processes to take place. Even though the Kuiper belt stretches across an enormous part of space, the combined mass of all the objects within it is surprisingly small. Scientists estimate that the so-called dynamically hot population, the group of objects that move in more tilted and elongated orbits, adds up to only about 1% of the Earth's mass. The dynamically cold population, which moves in more circular and stable orbits, is even smaller, holding only about 0.03% of the Earth's mass. Researchers believe that the hot population is what remains of a much larger collection of objects that originally formed closer to the Sun but were pushed outward when the giant planets migrated to their current positions. In contrast, the cold population is thought to have formed right where it is now, without much movement since the early days of the solar system. The most recent detailed calculation, published in the year 2018, estimated that the entire Kuiper belt has a mass of about 1/50th of Earth's mass. This estimate comes from measuring the tiny gravitational pull that the belt exerts on the orbits of the planets. However, this low total mass creates a puzzle for scientists. For large Kuiper belt objects, those bigger than about 100 kilometers, or roughly 62 miles across, to have formed, there would have needed to be much more material in that region during the early days of the solar system. If the cold Kuiper belt had always been as light and sparse as it is today, these big objects could not have formed simply through smaller bodies colliding and sticking together. On top of that, the tilted and eccentric orbits of many objects mean that collisions would often be violent, breaking things apart instead of helping them grow. It also seems unlikely that the cold population once had much more mass and later lost it. Neptune's gravitational pull today is far too weak to have cleared away such a huge amount of material, and the process of breaking down objects through countless collisions cannot explain it either. Since fragile binary systems still survive in the cold belt, they would not have lasted if collisions had been extremely destructive. Because of these issues, many scientists now think that the largest Kuiper belt objects may have formed in a different way, not from random collisions, but through the direct collapse of dense clouds of small icy pebbles. When it comes to the size of Kuiper belt objects, they follow certain mathematical patterns known as power laws. In simple terms, this means the number of objects depends on their size in a predictable way. The smaller the object, the more of them there are. Early studies, based on how bright these objects appear, suggested that for every one object between 200 and 400 kilometers wide, there are about 8 objects between 100 and 200 kilometers wide. More recent research has shown that the hot and cold populations of the Kuiper belt follow different patterns. Among the hot objects, large bodies follow a steep slope, meaning there are relatively few very large ones, while small ones are more common, with a turning point at about 110 kilometers. The cold objects show an even steeper slope for large bodies, with the change happening at about 140 kilometers. Other groups, such as the scattering objects, the Plutinos, which are in orbital resonance with Neptune, and the Neptune Trojans, show patterns similar to the hot population. Some of these groups may even show a sudden drop in numbers below a certain size, a feature scientists call a divot. This could mean that smaller bodies were later produced only as fragments from larger ones, or that the original population simply never formed many tiny objects to begin with. The very smallest Kuiper belt objects, those less than 1 kilometer across, are so faint that they cannot be seen directly, even with powerful telescopes like the Hubble Space Telescope. Instead, they have been detected through a method called stellar occultation, when one of these tiny objects briefly passes in front of a distant star, blocking its light for just a fraction of a second. In December of 2009, a team led by Hilke Schlisting reported finding such an object in archived Hubble data, taken in March of 2007. The object had an estimated radius of about 520 meters, meaning its diameter was just over 1 kilometer, and it blocked a star for only about 0.3 of a second. A follow-up study published in December of 2012 reported another occultation by a similar object with a radius of about 530 meters. From these rare events, the team concluded that there are far fewer sub-kilometer Kuiper Belt objects than scientists had previously expected based on the populations of larger bodies. Additional measurements came from NASA's New Horizons spacecraft, whose Venetia Burney student dust counter detected more dust particles, even out to 55 astronomical units from the Sun, than existing models predicted. This shows that we still do not fully understand how small debris and dust behave in this faraway region. Beyond the Kuiper Belt lies the scattered disk, a region that overlaps with the Kuiper Belt but stretches outward to more than 100 astronomical units from the Sun. Objects in the scattered disk follow very elongated and tilted orbits. According to most models, both Kuiper Belt objects and scattered disk objects first formed together in an early primordial belt. Later, Neptune's gravity sent some into stable orbits, the Kuiper Belt, and others into unstable ones, the scattered disk. Because of their unstable paths, many scientists believe that the scattered disk is the main birthplace of short-period comets. These icy bodies sometimes get nudged into the inner solar system, where they first become centaurs and later evolve into short-period comets. The Minor Planet Center, which keeps the official records of all trans-Neptunian objects, defines a Kuiper Belt object as anything that stays strictly within the Kuiper Belt's orbital zone. Anything beyond that is considered a scattered object. In practice, however, many scientists casually use the term Kuiper Belt objects to describe almost any icy world in the outer solar system, even if its orbit has carried it far beyond the belt itself. This is why Eris, which is actually a scattered disk object and even more massive than Pluto, is often called a Kuiper Belt object in conversation. Because of this overlap, astronomers still do not completely agree on the exact definition of the Kuiper Belt. Then, there are the centaurs. These bodies are not usually considered part of the Kuiper Belt because they were scattered inward toward the giant planets rather than outward. Still, the Minor Planet Center classifies both the centaurs and the scattered disk objects together as one broader family of scattered objects. During its long journey outward through the solar system, the planet Neptune is believed to have captured a wandering giant from the Kuiper Belt, Triton. Triton is extraordinary because it is the only large moon in the entire solar system that orbits its planet in a retrograde direction, meaning it travels the opposite way to Neptune's rotation. This unusual behaviour immediately signals that Triton was not born around Neptune. Unlike the great moons of Jupiter, Saturn and Uranus, which likely formed naturally from spinning disks of gas and dust that circled their young parent planets, Triton was already a fully formed body before Neptune seized it. But capturing such a large object is no simple task. For an object to be caught by a planet's gravity, it must somehow slow down during its encounter, otherwise it would simply fly past and escape. One widely accepted idea is that Triton was once part of a binary pair, two bodies orbiting each other. When it came too close to Neptune, the giant planet may have flung one member of the pair away into deep space while trapping Triton as its prize. This idea seems even more convincing because many Kuiper Belt objects, or KBOs, are known to exist as binaries. Triton is only about 14% larger than Pluto, and both worlds share striking similarities. Observations of their surfaces reveal that they are made of comparable materials, including frozen methane and carbon monoxide. All this strongly suggests that Triton was once a Kuiper Belt object, until Neptune claimed it during its period of migration. Since the beginning of the 21st century, astronomers have uncovered a growing family of large Kuiper Belt objects. Several of these new discoveries measure between 500 and 1,500 kilometers across, which is more than half the size of Pluto, whose diameter is about 2,370 kilometers. In the year 2002, scientists discovered Quaoar, a classical Kuiper Belt object over 1,200 kilometers wide. Just 3 years later, on the 29th of July 2005, two even larger objects, Makemake and Haumea, were announced. Others, such as Ixion, found in 2001, and Varuna, found in 2000, measure around 600 to 700 kilometers across. The appearance of so many Pluto-sized worlds forced astronomers to rethink Pluto's special status. These bodies not only rival Pluto in size, but many also have moons of their own, and they are composed of the same ices, such as methane and carbon monoxide. The situation echoed history. Just as the asteroid Ceres was first considered a planet until the discovery of countless other asteroids, Pluto now seemed to be one among many. The debate intensified with the discovery of Eris, a distant body in the scattered disk far beyond the Kuiper belt. Eris turned out to be 27% more massive than Pluto. At first, it was even believed to be physically larger in size, though the New Horizons mission later proved that Pluto is slightly wider, despite being lighter. Eris forced the International Astronomical Union, or IAU, to create a precise definition of what makes a planet. Their new rule declared that a true planet must clear the neighbourhood around its orbit. Because Pluto shares its space with many other large bodies in the Kuiper belt, it failed this test. In 2006, Pluto was officially reclassified as a dwarf planet, joining the very family of objects that had first challenged its uniqueness. Astronomers now wonder just how many Kuiper belt objects are large enough to be dwarf planets. Many candidates have surprisingly low densities, suggesting that fewer qualify than once thought. Still, most experts accept that Orcus, Haumea, Quaoar, Makemei, and of course Pluto belong to this special category. Others have put forward additional names such as Celesia, Mani, Aya, and Ixion. Among the trans-Neptunian objects, the six largest, Eris, Pluto, Gongong, Makemake, Haumea, and Quaoar, are all known to have moons. In fact, 2 of them have more than one. Larger Kuiper belt objects are more likely to host satellites than smaller ones, hinting at a different origin process. Another fascinating discovery is the high number of binaries in the Kuiper belt. Roughly 11% of KBOs exist as paired objects orbiting each other, the most famous example being the Pluto-Charon system. Exploration of this distant region began on the 19th of January 2006, when NASA launched the New Horizons spacecraft. After a 9.5-year journey, New Horizons flew past Pluto on the 14th of July 2015, delivering the first close-up views of the dwarf planet and its moons. But the mission did not stop there. Beyond Pluto, its goal was to explore even farther Kuiper belt objects. In October 2014, the Hubble Space Telescope identified 3 potential targets for the spacecraft, known simply as PT-1, PT-2, and PT-3, short for Potential Target 1, 2, and 3. These objects were tiny, with estimated diameters between 30 and 55 kilometers, far too small to be seen from Earth with ground-based telescopes. They circled the Sun at distances of 43 to 44 astronomical units, and mission planners calculated their chances of being reachable. PT-1 at 100%, PT-2 at only 7%, and PT-3 at 97%. PT-1, later given the designation 2014 MU69, and eventually named Arrokoth, became the chosen destination. In late 2015, New Horizons adjusted its course to aim for this small, primitive world. On the 1st of January 2019, the spacecraft flew past Arrokoth, revealing it to be a strange contact binary, 2 lobes fused together like a snowman, measuring about 32 kilometers long and 16 kilometers wide. Its surface appeared a deep red, the color of organic molecules altered by eons of cosmic radiation. Although New Horizons continues to send back data, no further missions are currently planned. Yet scientists are already dreaming of what could come next: orbiters or landers for Pluto, or new journeys to study Haumea and Makemake up close. Haumea in particular fascinates researchers because it is the parent body of a collisional family of objects, has 2 moons, and even a ring system. Engineers at Thales Alenia Space have studied how a spacecraft could be sent to orbit Haumea within 10 to 20 years of launch. Alan Stern, the principal investigator of New Horizons, has even suggested missions that might first fly past Uranus or Neptune before continuing onward to fresh Kuiper belt targets, reviving the excitement of the Voyager flybys of the 1980s. The Kuiper belt, once just a theory, is now a frontier alive with discovery. Each new object found adds another piece to the story of how the solar system was built and continues to evolve, far beyond the orbit of Neptune. Scientists have considered the distant world Quaoar as a possible stopover or flyby target for a space probe designed to eventually explore the mysterious interstellar medium, the vast space that lies between the stars. Quaoar happens to be located near a special region called the heliospheric nose, which is the part of the Sun's protective bubble that faces into the incoming flow of interstellar matter. Because of this, it would be an ideal stepping stone on the way out of the solar system. Pontus Brandt, a researcher at the Johns Hopkins Applied Physics Laboratory, along with his team, studied the idea of sending such a probe. Their plan involved the spacecraft first passing by Kuiper in the decade of the 2030s before continuing outward, straight through the heliospheric nose and into interstellar space. Kuiper is especially interesting to scientists because it seems to have a thin, fragile atmosphere made of methane that may be slowly vanishing into space, and it also shows signs of cryovolcanism, icy eruptions that work a bit like volcanoes, but with frozen material instead of molten rock. The proposed mission would launch on NASA's giant Space Launch System rocket. After launch, it would swing around Jupiter for a gravity assist and accelerate to an incredible speed of about 30 kilometers per second. There was also discussion of even more ambitious plans. Instead of just flying past, what if a probe actually orbited a Kuiper Belt object? In a study published in the year 2012, researchers calculated that two objects, Ixion and Huya, would be among the most practical choices for an orbiter. For example, they found that if a spacecraft were launched toward Ixion in the year 2039, it could arrive after about 17 years of travel. By the year 2006, astronomers had already discovered and clearly imaged dusty disks around 9 other stars beyond our Sun. These disks are thought to be the equivalent of the Kuiper Belt in other planetary systems. Interestingly, they fall into two main types. Some are wide belts, stretching out with radii greater than 50 astronomical units. Others are narrow belts, more like our own Kuiper Belt, with radii between 20 and 30 astronomical units, and with boundaries that appear sharp and well defined. Going further, astronomers estimate that between 15 and 20% of stars that are similar to our Sun show an unusual glow in infrared light. This glow is a telltale sign of massive dusty structures much like the Kuiper Belt. Most of the debris disks we know about are relatively young, but in January of the year 2006, the Hubble Space Telescope captured two especially important images. These two disks were much older, around 300 million years in age, and they had already settled into long-lasting stable shapes. One of the images shows a wide belt viewed from above, while the other shows a narrow belt seen from the side. Computer simulations of dust in our own Kuiper Belt suggest that, in its youth, the belt may have looked very different from how we see it today. Back then, it might have more closely resembled the delicate and narrow rings now being observed around much younger stars, a reminder that even our solar system once passed through a lively youthful stage. Alpha Centauri is a fascinating star system that shines brightly in the southern skies within the constellation called Centaurus. This system is not just one star, but actually a family of 3. The 3 stars are known as Rigil Kentaurus, also called Alpha Centauri A, Ptolemy, also called Alpha Centauri B, and the faint little star Proxima Centauri, also called Alpha Centauri C. Proxima Centauri holds a special place in astronomy because it is the closest star to our Sun. It sits at a distance of about 4.2465 light-years, which is the same as about 1.3020 parsecs. The other 2 stars, Alpha Centauri A and Alpha Centauri B, are the nearest stars that can be seen with the naked eye. Rigil Kentaurus and Ptolemy are very much like our Sun. Rigil Kentaurus belongs to the G class of stars, while Ptolemy is a cooler K class star. Together they form a binary star system known as Alpha Centauri AB. When we look at them from Earth without a telescope, they appear so close together that our eyes see them as a single point of light, shining with an impressive brightness. Their combined light has an apparent magnitude of about -0.27, making Alpha Centauri the brightest star in the Centaurus constellation and the 3rd brightest star in the entire night sky, only outshone by Sirius and Canopus. This pair of stars are also the closest binary stars to our Sun, lying at a distance of about 4.344 light-years, which equals 1.33 parsecs. Rigil Kentaurus is slightly larger and brighter than the Sun. It has about 1.1 times the mass of the Sun, and shines with about 1.5 times the Sun's brightness. Ptolemy, on the other hand, is a little smaller and dimmer, with about 0.9 times the Sun's mass and less than half the Sun's brightness. These 2 stars orbit around a shared centre of gravity, completing one full orbit every 79 years. Their orbit is not perfectly circular but elliptical, which means the distance between them changes. At their closest, they are about 11.2 astronomical units apart, which is roughly the distance from the Sun to Saturn. At their farthest, they are about 35.6 astronomical units apart, about the same distance from the Sun to Pluto. The third member of the family, Proxima Centauri, is a very small and faint red dwarf star of type M. It cannot be seen with the naked eye, yet it is even closer to us than Alpha Centauri AB, at a distance of about 4.24 light-years, or about 1.30 parsecs. Proxima orbits far away from the main pair of stars at a distance of about 13,000 astronomical units, which is about 0.21 light-years, or more than 400 times the size of Neptune's orbit around the Sun. Proxima Centauri has at least 2 known planets. One is called Proxima B, which is about the same size as Earth and orbits in the so-called habitable zone, where liquid water could theoretically exist, although conditions there are likely too harsh for life as we know it. The other is Proxima D, a much smaller sub-Earth planet that circles very close to the star. There is also a possible third planet called Proxima C, which would be a mini-Neptune orbiting about 1.5 astronomical units from Proxima, though its existence is still debated. Interestingly, Rigil Kentaurus may have a planet roughly the size of Saturn in its habitable zone, although scientists are not yet certain if it is truly a planet. Ptolemy, however, has no confirmed planets. The name Alpha Centauri comes from its scientific designation, given by Johann Bayer in the year 1603. The constellation Centaurus, to which it belongs, is named after the centaur from Greek mythology, a creature that was half man and half horse. According to myth, the hero Heracles accidentally wounded the centaur and later placed him among the stars after his death. In the sky, Alpha Centauri marks the right front hoof of the centaur figure. The name Rigil Kentaurus is a Latinized form of the Arabic phrase Rigil al-Kintarus, which means the foot of the centaur. The word Kintarus itself is the Arabic form of the original Greek word Kentaurus. Sometimes the star is simply called Rigil Kent, or even just Rigil, though the name Rigil is also used for another famous star, Rumjil, in the constellation Orion. The alternative name Ptolemy also comes from Arabic origins. It was linked to the word as Zalaman, meaning the 2 ostriches. Ancient scholars, including Zakaria al-Qazwini, once applied this name to a different pair of stars in the Sagittarius constellation, but over time the name shifted and was associated with Alpha Centauri. Later, in the year 1669, Jacob Golius used the name in his Latin translation of Alfagani's writings, further spreading its use in Europe. Proxima Centauri, the faint red dwarf, was not known until much later. It was discovered in the year 1915 by the Scottish astronomer Robert Innes, who realised it was even closer to us than Alpha Centauri AB. He suggested the name Proxima Centaurus, which in Latin means the nearest star of Centaurus. Over time, the shorter name Proxima Centauri became common and is now officially recognised by the International Astronomical Union, often simply shortened to Proxima. In the year 2016, the International Astronomical Union decided that proper names should be given to each star individually, rather than to entire systems. That year, they officially confirmed Rigil Kentaurus as the name for Alpha Centauri A, Proxima Centauri for Alpha Centauri C, and later in August of the year 2018, the name Ptolemy was approved for Alpha Centauri B. Other names for the system have appeared throughout history. In the 19th century, the American sky popularizer Elijah H. Burritt called it Bungala, though the origin of that name is still uncertain. It may have been inspired by the Greek letter beta and the Latin word ungula, meaning hoof. Different cultures have also given their own names to this bright star system. In Chinese astronomy, Alpha Centauri together with Epsilon Centauri formed an asterism called Nanmen, or Southern Gate. Thus, Alpha Centauri itself was called Nanmen meaning the second star of the Southern Gate. Among the indigenous Burong people of northwestern Victoria in Australia, Alpha Centauri and Beta Centauri are remembered as 2 heroic brothers called Burmbamel, who fought and killed Chingal, the Emmu, represented in the sky by the Coalsack Nebula. In another local language, Wotjobaluk, the pair were called Bram Bram Bolt. When seen with the naked eye, Alpha Centauri A and Alpha Centauri B look like a single brilliant star, shining as the brightest jewel in the southern constellation known as Centaurus. In truth, they are a pair of stars locked in a cosmic dance. To our eyes, their apparent closeness changes slowly over a cycle of about 80 years. Sometimes they seem to be separated by only about 2 arcseconds, while at other times they appear as far apart as 22 arcseconds. For comparison, the human eye can usually distinguish details down to about 60 arcseconds. This means that for most of their long orbit, the 2 stars can be easily separated using nothing more than binoculars or a small telescope. Together, Alpha Centauri A and B shine with a combined brightness of about -0.27 in apparent magnitude. This places them firmly among the so-called first magnitude stars, which are the brightest stars in the sky. Only Sirius, the brightest star of all, and Canopus, the great beacon of the southern skies, outshine them. Alpha Centauri is also one of the famous pair of stars known as the Pointers, or the Southern Pointers. Along with its companion Beta Centauri, also called Hadar or Agena, this pair directs the eye toward the Southern Cross, the constellation Crux. This guiding line helps observers easily distinguish the true Southern Cross from a deceptive nearby grouping of stars called the False Cross. For people living south of about 29 degrees south latitude, Alpha Centauri never dips below the horizon. It is a circumpolar star, always present in the night sky. But for those living north of about 29 degrees north latitude, the star never rises at all. Between these regions, from about 29 degrees north down to the equator, the star can just be seen hugging the southern horizon for a short time each year when it culminates. This is the case for cities such as Hermosillo and Chihuahua in Mexico, Galveston in Texas, Ocala in Florida, and the island of Lanzarote in Spain's Canary Islands. Each year, Alpha Centauri reaches its highest point in the sky at midnight on the 24th of April and at 9 o'clock in the evening on the 8th of June. Not far away in the sky, Proxima Centauri, the faint third member of the Alpha Centauri system, lies about 2.2 degrees to the southwest. This separation is about 4 times wider than the Moon's apparent size. Proxima Centauri appears as a dim, deep red star with a typical brightness of magnitude 11.1. Because it is faint and lies in a relatively empty part of the sky, one needs a moderately large telescope to glimpse it. Catalogued as V645 Centauri in the General Catalogue of Variable Stars, version 4.2, it belongs to a class of stars known as flare stars. These are unstable stars that can suddenly brighten by as much as 0.6 magnitude within minutes before fading again. Amateur and professional astronomers alike often monitor Proxima using optical telescopes or even radio telescopes, hoping to catch one of these outbursts. In August of the year 2015, Proxima produced its largest recorded flares, briefly glowing 8.3 times brighter than usual on the 13th of August in the blue region of the spectrum. Alpha Centauri's fame stretches back to ancient times. The great astronomer Claudius Ptolemy included it in his star catalogue of the 2nd century, known as the Almagest. He recorded its ecliptic coordinates, though surviving manuscripts disagree slightly, some giving its latitude as 44 degrees 10 minutes south, others as 41 degrees 10 minutes south. Today, its ecliptic latitude is about 43.5 degrees south, shifted slightly since Ptolemy's day due to the star's slow proper motion. In Ptolemy's era, Alpha Centauri could still be seen from Alexandria in Egypt at latitude 31 degrees north. Now, because of the slow wobble of Earth's axis known as precession, the star's position has shifted, and it can no longer be seen from there. In the year 1592, the English explorer Robert Hughes introduced Alpha Centauri to European scholars in his book Tractatus de Globis. He described it alongside Canopus and Achernar as one of only 3 first-magnitude stars that could never be seen from England. He placed Alpha Centauri in the right foot of the Centaur. A century later, in December of 1689, the French astronomer Jean Richaud, while watching a comet from the Indian city of Puducherry, realized that Alpha Centauri was not 1 star but 2. This discovery made Alpha Centauri only the 3rd binary star ever recognized, after Mizar in Ursa Major and Crux in the Southern Cross. The large proper motion of the system, its slow but noticeable drift across the sky, was first recognized by Manuel John Johnson, observing from the island of St. Helena. He communicated his findings to Thomas Henderson at the Royal Observatory in Cape Town, South Africa. Henderson then made extremely careful measurements of the parallax of Alpha Centauri, between April of 1832 and May of 1833. At first, he doubted his results, thinking them too large to be correct, and delayed publishing them. Eventually, in 1839, he released his work after Friedrich Bessel had published the parallax of 61 Cygni in 1838. Because of this, Alpha Centauri is sometimes considered the second star whose distance was measured, even though Henderson had been first. Today, we know Alpha Centauri lies about 4.396 light-years away, or roughly 41,590 billion kilometers. In 1834, John Herschel made the first micrometrical measurements of the system, and in the early 20th century astronomers began to use photographic plates for greater accuracy. By the year 1926, William Stephen Finson had already calculated orbital elements close to the ones accepted today, allowing astronomers to predict the star's positions with high precision. Later, in the year 2002, D. Pourbet further refined these orbital details. The third star, Proxima Centauri, was discovered much later in 1915 by the Scottish astronomer Robert Thorburn Ayton Innes. By comparing photographic plates taken at different times, he noticed that this faint red star showed the same large proper motion and parallax as Alpha Centauri A and B, only slightly closer. From this, he concluded that Proxima was a true companion to the system, and the nearest star to Earth known at that time. Alpha Centauri, the star system closest to our Sun, may lie inside a region of space called the G cloud, which is part of the much larger local bubble of interstellar gas. The nearest known stellar system to Alpha Centauri is a pair of faint brown dwarfs, known together as Lumen 16. This unusual double system lies at a distance of about 3 6/10 light-years, or a little more than 1 parsec, from Alpha Centauri. All of the stars in Alpha Centauri show what astronomers call proper motion. This means that, over many years and centuries, their positions slowly shift against the background stars of the sky. Ancient astronomers, who did not know about proper motion, assumed that the stars were fixed permanently on a giant crystalline sphere surrounding Earth, an idea famously described by the philosopher Aristotle. It was not until the year 1718 that the English astronomer Edmund Halley noticed that certain bright stars had clearly moved since the days of the ancient Greek star catalogues. A little more than a century later, in the 1830s, the Scottish astronomer Thomas Henderson studied Alpha Centauri using a large mural circle for precise measurements. He discovered the true distance to the star system, making Alpha Centauri the very first star, other than the Sun, to have its distance correctly measured. Henderson also noticed that this system must have a particularly strong proper motion. To confirm this, he compared his results with the much earlier observations made by the French astronomer Nicolas Louis de Lacaille in the years 1751 to 1752. The difference between the two sets of measurements proved that Alpha Centauri was indeed moving swiftly across the heavens. Modern calculations show that the combined centre of mass of Alpha Centauri A and B moves across the sky at about 3,620 milliseconds per year toward the west and 694 milliseconds per year toward the north. This produces an overall motion of about 3,686 milliseconds per year in a direction that is about 11 degrees north of west. Put more simply, the pair shifts by about 6 arc minutes every century, or a little more than 1 degree every 1,000 years. In terms of actual speed through space, Alpha Centauri AB travels at about 23 km per second to the west, and about 4 4/10 km per second to the north. Spectroscopic studies also reveal that the system is moving toward our solar system at about 22 4/10 km per second. Altogether, Alpha Centauri is flying through space at a total speed of about 32 4/10 km per second relative to the Sun. This speed is close to the average for nearby stars, because Alpha Centauri AB lies almost exactly in the same plane as the Milky Way when seen from Earth. Many distant stars can be seen directly behind it. This alignment occasionally creates special opportunities for astronomy. For example, in early May of the year 2028, Alpha Centauri A will pass in front of a remote red star catalogued as 2 mass 1,439,616,64928. There is about a 45% chance that the light of that distant star will be bent into a dazzling ring of light, known as an Einstein ring by the gravity of Alpha Centauri. Other such alignments will happen in the future, allowing scientists to refine measurements of motion and perhaps even detect planets around these stars. Over the coming millennia, Alpha Centauri will continue to shift its place in the sky. Around the year 6200 of the Common Era, it will appear in a rare and spectacular close conjunction with Beta Centauri, forming a brilliant double star in the southern sky. Later, it will move northward past the famous Southern Cross and slowly climb toward the celestial equator. By around the year 26,700, in the present-day constellation of Hydra, Alpha Centauri will come closer to our solar system than ever before, just about 9/10 of a parsec, or roughly 2 9/10 light-years away. Some newer calculations place this closest approach a few centuries later, around the year 27,000. At that time, Alpha Centauri will shine even brighter than it does today, with a magnitude of about -0.86, almost as bright as Canopus. Yet even then, it will not outshine Sirius, which will remain the brightest star in Earth's sky, apart from the Sun, for the next 60,000 years and more, continuing to hold that title for about 210,000 years into the future. Alpha Centauri is not a single star but a triple system. Its two brightest members, Alpha Centauri A and Alpha Centauri B, form a close binary pair that orbit around a common centre of mass. Astronomers often call this pair Alpha Centauri AB, and sometimes write it as AX-B. The faint red dwarf Proxima Centauri, also called Alpha Centauri C, orbits much farther out, making the system a true trio. Because Proxima is almost equally distant from Alpha Centauri A and B, scientists sometimes treat the inner binary pair as if it were a single gravitational body when considering Proxima's orbit. Alpha Centauri A and B take almost exactly 79 3/4 years to complete one orbit around one another. Their orbit is not a perfect circle but rather an ellipse, with a moderate eccentricity of about 0.52. At their closest approach, called periastron, the two stars are separated by about 11 2/10 astronomical units, a distance comparable to that between the Sun and Saturn. At their farthest distance, called a pastron, they are about 35 6/10 astronomical units apart, similar to the Sun's distance from Pluto. The most recent periastron occurred in August of the year 1955, and the next will happen in May of the year 2035. Their most recent apastron took place in May of the year 1995, and the next will come in the year 2075. From Earth, we see the star's apparent orbit projected against the sky, which means their separation and position angle constantly change. For instance, in the year 2019, the stars were about 4 92/100 arc-seconds apart, at a position angle of 337 1/10 degrees. By the year 2020, their separation increased to about 5 49/100 arc-seconds at a position angle of 345 3/10 degrees. Their closest recent approach was in February of the year 2016, when they were only 4 arc-seconds apart at a position angle of 300 degrees. At their widest, Alpha Centauri A and B can be seen about 22 arc-seconds apart, while at their narrowest they shrink to about 1 7/10 arc-seconds. The last time they were widely separated was in February of the year 1976, and the next maximum separation will be in January of the year 2056. Farther away, Proxima Centauri lies at a distance of about 13,000 astronomical units, or about 2/10 of a light-year from the central pair. This distance is about 5% of the distance between Alpha Centauri AB and our Sun. For many years, astronomers were not sure whether Proxima was truly gravitationally bound to Alpha Centauri AB, or merely a star passing nearby. In the year 2017, precise measurements of Proxima's motion finally showed that it is indeed bound to the system. The orbit of Proxima Centauri around the central pair is vast and highly elongated. Its orbital period is roughly 511,000 years, give or take several tens of thousands. At its closest, Proxima comes to about 4,100 astronomical units from Alpha Centauri AB, while at its farthest it stretches out to about 12,300 astronomical units. This makes its orbit far more eccentric than that of Mercury in our own solar system, giving Proxima a strange and wandering path around its brighter siblings. Scientists have studied the Alpha Centauri system with many different methods, including astroseismology, which looks at vibrations inside stars, measurements of chromospheric activity, and studies of stellar rotation, also called gyrochronology. All of these different approaches point to the same conclusion. Alpha Centauri is very similar in age to our Sun, or perhaps a little older. When researchers used precise observational data to analyse the vibrations of the Alpha Centauri stars, they came up with several possible age estimates. Some studies suggested about 4.85 billion years, with an uncertainty of 500 million years. Others gave 5 billion years with the same margin of error, and still others found 5.2 billion years, with an uncertainty of nearly 2 billion years. Some estimates placed the system at 6.4 billion years, while the most precise of all gave 6.52 billion years, with only 300 million years of uncertainty. Looking at chromospheric activity, essentially the behaviour of calcium emissions from the stars, gave an age of around 4.4 billion years, though with a large uncertainty of about 2.1 billion years. Gyrochronology, which compares the star's rotation with known stellar aging patterns, gave an age of about 5 billion years with a margin of only 300 million years. Theoretical models of how stars evolve also support the idea that both Alpha Centauri A and B are slightly older than the Sun, falling somewhere between 5 and 6 billion years of age. By studying the orbital motion of the two main stars, astronomers calculated their combined mass at about twice that of the Sun. Separately, Alpha Centauri A has a mass of about 1.08 times the Sun's, while Alpha Centauri B has about 0.91 times the Sun's mass. Some other studies suggest slightly different numbers, with Alpha Centauri A weighing in at 1.14 solar masses and B at 0.92, bringing the total to about 2.06 solar masses. In terms of brightness, Alpha Centauri A shines with an absolute magnitude of about plus 4.38, while Alpha Centauri B has a magnitude of plus 5.71. Alpha Centauri A, also called Rigil Kentaurus, is the brighter and more massive of the pair. It is a yellowish star, very much like our Sun, classified as a G2 main sequence star. It is about 10% heavier than the Sun and has a radius about 22% larger. In the night sky, it is one of the brightest stars, ranking 4th overall with an apparent magnitude just above 0. It is only a touch fainter than Arcturus, which has a magnitude slightly below 0. Like the Sun, Alpha Centauri A shows magnetic activity such as sunspot-like regions, and coronal changes linked to its rotation, but since the year 2005 its activity has dipped into a very quiet phase, possibly similar to the famous Maunder minimum that the Sun experienced centuries ago. Some astronomers suggest this is part of an extremely long stellar activity cycle, and that the star may slowly be recovering. Alpha Centauri B, also called Ptolemy, is the smaller and slightly cooler companion. It is an orange K1 main sequence star with about 90% of the Sun's mass, and a diameter that is 14% smaller. Though it shines less brightly in visible light than Alpha Centauri A, it actually gives off more energy in the X-ray part of the spectrum. Its brightness changes more noticeably over short periods, and at least one flare has been observed. Alpha Centauri B is more magnetically active than Alpha Centauri A, showing an activity cycle of about 8.2 years, compared with the Sun's 11-year cycle. Later measurements suggested a slightly shorter cycle of 7.8 years. Its brightness in the sky, at magnitude plus 1.35, makes it just a little dimmer than the star Mimosa. The third member of the system, Alpha Centauri C, better known as Proxima Centauri, is a tiny red dwarf star. It belongs to the M6 spectral class and shines incredibly faintly, with an absolute magnitude of plus 15.6, which is over 20,000 times dimmer than the Sun. It has only about 12% of the Sun's mass. Despite being the closest star to us after the Sun itself, Proxima is too faint to be seen without a telescope. So far, astronomers have confirmed 2 planets in the Alpha Centauri system, both orbiting Proxima Centauri. Many more have been suggested around all 3 stars, but most of those claims have not held up. In the year 2021, a candidate planet nicknamed Candidate 1 was detected around Alpha Centauri A. It seemed to orbit at about 1.1 astronomical units, roughly the distance between Earth and the Sun, with a period of about 1 year. Its size was estimated to be somewhere between that of Neptune and half that of Saturn. However, it might not be a planet at all, but instead a dust disk or an observational artifact. Later studies ruled out the possibility that it was just a background star. If confirmed, this candidate would likely be officially named Alpha Centauri AB. The James Webb Space Telescope has been assigned to search for planets in the Alpha Centauri system. Its first coronagraphic observations in July of 2023 did not succeed, but more attempts were scheduled for March of 2024. Based on its sensitivity, Webb is expected to detect planets as small as 3 to 5 times the size of Earth at distances between 0.5 and 3 astronomical units from Alpha Centauri A. In August of 2024, Webb spotted a faint source of light about 2 astronomical units away from Alpha Centauri A. This could be the same candidate planet reported in 2021. The object is unlikely to be an artifact, but more observations are needed to confirm it as a planet. If it truly is one, it would likely weigh between 90 and 150 times the mass of Earth, be about the size of Jupiter, and have a very cold temperature of about -48 degrees Celsius. The first major claim of a planet around Alpha Centauri B came in the year 2012, when astronomers thought they had found a planet roughly the size of Earth orbiting every 3.2 days. However, this was disproven in 2015, when the signal was shown to be caused by the way the data was processed. Another search using the Hubble Space Telescope between 2013 and 2014 detected a possible transit that may belong to a different small planet around Alpha Centauri B. This object might be less than Earth's size and could circle the star every 12 to 20 days. If it exists, it would likely be covered in lakes of molten lava and far too hot to support life. But this discovery too remains unconfirmed. The most promising planet in the system remains Proxima Centauri B, discovered in 2016 by the European Southern Observatory. This world is just a little heavier than Earth and orbits very close to Proxima Centauri, inside its habitable zone, where liquid water could exist. The discovery of a possible planet named Proxima Centauri C was first made public in the year 2020. This mysterious world could either be a so-called super-Earth, which is a rocky planet larger than Earth, or a mini-Neptune, a smaller version of the icy giant Neptune. Astronomers estimated its mass to be around 7 times that of Earth. It seemed to orbit its host star, Proxima Centauri, at a distance of about 1.5 astronomical units, which means about 1.5 times the distance between Earth and the Sun. Completing one full orbit was thought to take nearly 1,928 days, just over 5 years. In June of 2020, astronomers even believed they might have caught a direct image of this planet, and some thought it could be surrounded by a vast ring system. However, excitement quickly met with doubt. By the year 2022, new research questioned whether Proxima C even existed at all. And as of the year 2025, the evidence still remains uncertain. Observations made with an advanced instrument called the NURBS spectrograph failed to confirm the planet, though they did detect a faint signal with a similar orbital rhythm, hinting that something might still be there, but not as massive as once believed. Another study in the year 2020 tried to refine the mass of the already known planet Proxima b. This research ruled out the presence of any additional planets larger than about 6/10 the mass of Earth, with short orbital periods of less than 50 days. But, to their surprise, the astronomers did detect a very subtle radial velocity signal repeating every 5.15 days. This suggested the existence of a tiny planet with a mass of less than 1/3 that of Earth. This new world, later called Proxima Centauri d, was first announced in the year 2022 and officially confirmed in the year 2025. The possibility of other planets in the Alpha Centauri system has long fascinated astronomers. These could be orbiting either Alpha Centauri A or Alpha Centauri B individually, or perhaps even both stars in a wide orbit. Because Alpha Centauri A and B are so similar to our Sun in age, chemistry and brightness, planet hunting teams have been especially determined to search these stars for Earth-like worlds. Using advanced methods like radial velocity tracking and star transit observations, astronomers have carefully studied both stars. So far, no evidence has been found for large gas giants or brown dwarfs circling either of them. In the year 2009, computer simulations suggested that a planet could have formed within the habitable zone of Alpha Centauri b. This zone, where liquid water could exist on a planet's surface, stretches from about half an astronomical unit to nearly 9/10 of an astronomical unit from the star. Some models even propose that if Alpha Centauri A and B had originally been farther apart and later moved closer, something possible if they were born in a crowded star cluster, then the conditions for forming planets could have been even more favourable. Around Alpha Centauri A, planets might form slightly farther out, because its stronger gravity would allow stable orbits at greater distances. The fact that neither Alpha Centauri A nor B hosts close-orbiting gas giants or brown dwarfs is actually encouraging. Without these massive planets disrupting their systems, the chances of smaller, rocky, Earth-like planets forming is thought to be much higher. Theoretical studies suggest that, with the right sensitivity, astronomers might one day detect a planet about 1.8 times the mass of Earth within Alpha Centauri B's habitable zone. Sophisticated measurements of Alpha Centauri B, made using the highly precise HARP spectrograph, short for High Accuracy Radial Velocity Planet Searcher, should have been able to detect planets with masses of about 4 times that of Earth and orbital periods of about 200 days, exactly the kind of worlds that could be in the habitable zone. Yet, no such planets were found. Even so, astronomers estimate that there is still a very high chance, around 75%, that at least one Earth-like planet could exist somewhere within the Alpha Centauri system. Current detection thresholds suggest that planets as small as about 53 Earth masses could be spotted around Alpha Centauri A, about 8 Earth masses around Alpha Centauri B, and less than half an Earth mass around Proxima Centauri. Early computer models once confidently predicted that terrestrial planets should exist around both Alpha Centauri A and Alpha Centauri B. More recent and complex simulations, however, revealed that the constant gravitational tug-of-war between these two stars makes planet formation much harder than first imagined. Yet despite these difficulties, many astronomers believe Alpha Centauri still remains one of the best possible places to look for alien life beyond our solar system. Its stars are so much like our Sun, and their long-term orbital stability could easily provide the calm, steady conditions needed for life to flourish. Turning to our own solar system for comparison, scientists once thought that the giant planets Jupiter and Saturn had played a vital role in guiding comets into the inner system, delivering precious water and ices to the young Earth and its neighbouring planets. But later, more detailed measurements of the deuterium to hydrogen ratio in several comets, including Halley, Hyakutake, Hale-Bopp T7 of 2002 and Tuttle, revealed that their water had nearly twice the ratio found in Earth's oceans. This discovery suggested that comets supplied less than 1/10 of Earth's water, with most of it coming from other sources. In a similar way, Proxima Centauri might have influenced the early planetary disk of the Alpha Centauri system, enriching the region with icy materials. However, this idea could be challenged if Alpha Centauri A or B happened to harbour hidden gas giants that stirred their own cometary populations, just as Jupiter and Saturn are thought to have done in our solar system. It is also likely that Alpha Centauri, like our own Sun, has a distant Oort cloud filled with icy bodies. From time to time, passing stars or gravitational interactions with giant planets can disturb these clouds, sending frozen comets plunging inward toward their stars. The same scenario could one day occur in our solar system if Alpha Centauri or another nearby star passes close enough, disturbing our own Oort cloud and flooding the skies with a fresh wave of comets. Between the years 2007 and 2012, astronomers carefully observed Alpha Centauri A and B and noticed something unusual. In the mid to far infrared band, particularly around the wavelength of 24 micrometers, they detected a slight excess of radiation. This faint glow could mean that there is a thin ring of dust, or even a very sparse disk of debris circling the stars. The total amount of material, however, would be very small, only between 1/10,000,000th and 1/1,000,000th of the Moon's mass. That is roughly 10 to 100 times more than the mass of the zodiacal cloud, which is the thin dust spread throughout our own solar system. If such dusty disks truly exist, then around Alpha Centauri A it would likely remain stable, only up to about 2 8/10 astronomical units from the star, while Alpha Centauri B's disk would be stable up to about 2 5/10 astronomical units. This means that the entire disk around star A would stay inside the so-called frost line, where water and other volatile materials cannot freeze, In contrast, the disk around star B would extend just a little beyond that icy boundary. Some researchers have even suggested that material from such disks might not remain trapped there. Instead, it could be exchanged with the far outer parts of our own solar system, meaning that dust or debris from Alpha Centauri could, in theory, drift toward us, and vice versa. If this were proven true, it would suggest that stars and planetary systems across the galaxy might be connected by a vast web of shared material. The night sky, as seen from Alpha Centauri A or B, would look surprisingly familiar to us on Earth, but with one striking difference. The brightest star in the constellation Centaurus, which from Earth is Alpha Centauri itself, would no longer be there. From that vantage point, the Sun would instead take its place. To an observer near Alpha Centauri, the Sun would shine as a white star of magnitude plus 0.5, about the same brightness that Betelgeuse appears to us here on Earth. It would be located in the constellation Cassiopeia, in the eastern part of the sky, very close to the Heart Nebula. There, the familiar W shape of Cassiopeia's stars would appear slightly altered, bent into something that looked more like /W. Other well-known stars would also shift their positions in dramatic ways. Sirius, the brightest star in Earth's night sky, would still hold that honour when seen from Alpha Centauri. At a distance of about 9 2/10 light-years, it would shine with a magnitude of -1.2. But instead of being in Canis Major, it would appear in the constellation Orion, less than a single degree away from Betelgeuse. Procyon, another bright nearby star, would also change its place and would appear to outshine Pollux in the constellation Gemini. If there were an Earth-like planet orbiting Alpha Centauri A, at about 1 1/4 astronomical units from its star, a distance where the planet would take a little over 1 1/3 years to complete a single orbit, it would receive light very similar to what Earth gets from the Sun. From this planet's sky, Alpha Centauri B would appear as a dazzling second star. Though much dimmer than the primary, it would still shine hundreds to thousands of times brighter than the full moon looks to us on Earth. The reverse would also be true. A planet circling Alpha Centauri B at about 7/10 of an astronomical unit would see Alpha Centauri A as a brilliant companion star, glowing far brighter than the moon in our night sky. Proxima Centauri, the third and smaller member of the system, would be far less impressive when seen from such planets. At its usual distance, it would only appear as a faint star of magnitude 4 1/2, though during its closest approach, called periastron, it would brighten slightly to magnitude 2 6/10. Because of its closeness to Earth, Alpha Centauri has long been considered a prime target for future exploration, either robotic or even crewed missions. With today's conventional spacecraft, such a journey would take many thousands of years. But with advanced concepts, such as nuclear pulse propulsion, or the use of powerful laser-driven light sails, like those proposed in the Breakthrough Starshot project, the trip could be shortened to about 20 years. The goal of such a mission would be to fly past Alpha Centauri and capture photographs of any planets orbiting its stars. One especially intriguing target would be Proxima Centauri B, a planet discovered in August of 2016 by the European Southern Observatory. NASA itself once outlined a bold mission plan. In the year 2017, it suggested launching a probe toward Alpha Centauri in the year 2069 to mark the 100th anniversary of the Apollo 11 moon landing of 1969. If the spacecraft could reach 10% of the speed of light, about 108 million kilometers per hour, it would arrive at Alpha Centauri in the year 2113, 44 years after launch. The first signals from the probe would then take another 4 years to travel back to Earth, arriving in the year 2117. Unfortunately, after this idea was published, it received no further development or funding. Barnard star is a small and faint red dwarf star located in the constellation of Ophiuchus, the Serpent Bearer. It lies at a distance of almost 6 light-years from Earth, or about 1 4/5 parsecs. This makes it the 4th closest known individual star to the Sun, coming right after the 3 stars of the Alpha Centauri system. It also holds the title of being the nearest star in the northern half of the sky. In terms of size, Barnard's star is tiny compared to our Sun. Its mass is only about 1/6 that of the Sun, and its diameter is less than 1/5 of the Sun's. Despite being one of our closest stellar neighbours, it is so faint that it cannot be seen without a telescope. Its apparent brightness, or visual magnitude, is a little less than +10, which is far too dim for the naked eye to detect. Interestingly, while it is very weak in visible light, it shines more strongly in the infrared part of the spectrum. Because of its closeness and its position near the celestial equator, Barnard's star has become one of the most closely studied red dwarfs in astronomy. For more than a century, researchers have examined its characteristics, carefully measured its movement, and searched for possible planets in orbit around it. Even though Barnard's star is extremely old, it is still not completely quiet. On rare occasions, it erupts with sudden flares. In the year 1998, astronomers observed one such powerful flare, proving that the star still has a surprising level of activity. Barnard's star has been found to host a system of small planets. 4 sub-Earth mass planets orbit close to the star. The first of these, Barnard's star B, was discovered in the year 2024, and 3 more planets were confirmed in the following year, 2025. Earlier in history, there had been many claims of larger planets circling the star, but these were eventually proven false. The star was named after Edward Emerson Barnard, an American astronomer. In the year 1916, Barnard measured its astonishingly high proper motion, more than 10 arcseconds every year when compared to the Sun. This is the fastest proper motion of any known star. Long before this measurement, the star had already appeared on photographic plates taken at Harvard University in the years 1888 and 1890. In the year 2016, the International Astronomical Union formed a special group to standardize star names. On the first day of February in the year 2017, the name Barnard's star was officially approved and added to the Union's official list of star names. Barnard's star belongs to the spectral type known as M4, making it a cool and faint red dwarf. It is far too dim to be seen without a telescope. Astronomers estimate its age to be between 7 and 12 billion years, which is much older than our Sun's age of about 4.5 billion years. It may even be among the oldest stars in the entire Milky Way galaxy. Over time, Barnard's star has lost much of its rotational energy. Careful studies of tiny changes in its brightness reveal that it takes about 130 days to complete a single rotation, whereas the Sun spins once in only about 25 days. For a long time, astronomers believed the star was inactive, but the flare seen in 1998 proved otherwise. As a result, Barnard's star is now classified as a flare star. In fact, it even has its own designation as a variable star, V2500 Ophiuchi. In the year 2003, it became the first star where astronomers were able to detect a change in radial velocity caused by its motion. Later measurements showed that this variability was due to the star's own activity. The motion of Barnard's star across the sky is so rapid that it corresponds to a sideways speed of about 90 kilometers per second. Over the course of a human lifetime, this amounts to the star shifting 1/4 of a degree across the heavens, roughly half the width of the full moon as seen from Earth. Its radial velocity, the speed at which it is moving toward us, is about -110 kilometers per second. When combined with its sideways speed and distance, this gives it a true space velocity of about 143 kilometers per second relative to the Sun. In the far future, around the year 11,800 of the Common Era, Barnard's star will make its closest approach to the Sun, coming to within roughly 3¾ light years. Even then, it will not surpass Proxima Centauri as the nearest star, because by that time Proxima will have moved even closer. At its closest pass, Barnard's star will still be invisible to the unaided eye. Its brightness will increase slightly, rising by about 1 magnitude, but it will remain 2.5 magnitudes too dim to be seen without a telescope. In physical terms, Barnard's star has about 1/6 the mass of the Sun and about 1/5 the Sun's radius. While it has around 150 times the mass of Jupiter, its radius is only about twice as large, meaning that its material is packed extremely densely. Its surface temperature is about 3,200 Kelvin, and its overall brightness is only about 3,000ths that of the Sun. If Barnard's star were placed at the same distance from Earth as the Sun, it would appear only about 100 times brighter than the full moon, far dimmer than our Sun actually looks. The star's composition, or metallicity, lies somewhere between 10 and 30% of the Sun's. In astronomy, Metals are all elements heavier than helium, and metallicity helps categorize stars as belonging to different populations. Barnard's star seems to belong to the second stellar population, called Population 2, which generally consists of older metal-poor stars. However, its metallicity is slightly higher than that of typical halo stars, and instead matches the low end of the disk star population. Because of this, scientists often call it an intermediate Population 2 star. Some recent research has suggested that its metallicity might even be close to the Sun's, ranging from 3/4 to slightly above the Sun's own level. In August of the year 2024, astronomers made a major breakthrough in the long and often controversial search for planets around Barnard's star. By carefully analysing data collected with the powerful espresso spectrograph attached to the European Southern Observatory's Very Large Telescope, they were able to confirm the existence of a planet. This world has a minimum mass of about 0.37 times the mass of Earth, with an uncertainty of plus or minus 0.05 Earth masses, and it completes one orbit around Barnard's star in just 3.15 days. This discovery marked the very first solid and convincing evidence that Barnard's star truly does host at least one planet. The newly confirmed planet was given the name Barnard Star B, or simply Barnard B. Interestingly, this designation had already been used years earlier for a different planet candidate that was later shown not to exist, so the name was reused. Alongside this confirmation, the same study also proposed the possible presence of 3 additional low-mass planets. All 4 of these worlds orbit extremely close to their parent star, much closer than the region known as the habitable zone, the area where liquid water could potentially exist on a planet's surface. Observations of the star by NASA's TESS space telescope revealed no planetary transits, meaning that from our viewpoint on Earth, the system is not aligned edge-on, so the planets do not pass directly in front of the star. In March of the year 2025, an independent follow-up study confirmed the existence of all 4 planets. The new data was so precise that they also ruled out the possibility of any additional planets larger than 0.57 Earth masses existing within Barnard's star's habitable zone, with 99% confidence. Among the confirmed worlds, the one named Barnard Star E turned out to be especially remarkable. It has a minimum mass of only 0.193 times that of Earth, making it the lightest planet ever detected by the radial velocity method. The best mathematical fit to the orbital data suggested that these planets travel in slightly oval or eccentric orbits. However, computer simulations showed that such eccentric paths would be unstable, while circular orbits would remain stable for long periods. This means the eccentricities might have been exaggerated by the data, and the planets could, in reality, have nearly circular paths around their star. The excitement of these findings is even more striking when compared with Barnard's star's long and controversial history. Over the decades, many claims of planets around it have been made, only to be disproven later. Between the early 1960s and the early 1970s, the Dutch astronomer Peter van der Kamp argued repeatedly that Barnard's star had planets. He believed he had found evidence of large gas giants orbiting the star, but his specific claims were finally disproven in the mid-1970s after years of heated debate. Even as recently as November of the year 2018, an international team announced what looked like the detection of a super-Earth planet orbiting Barnard's star. This candidate was thought to have a minimum mass of about 3.2 times that of Earth, and to orbit the star once every 233 days at a distance of about 0.4 astronomical units. It was believed to be a cold world, with an estimated surface temperature near minus 170 degrees Celsius, or minus 274 degrees Fahrenheit. Some scientists even thought it might be directly imaged within a decade. However, in July of the year 2021, this claim was refuted when researchers found that the supposed planetary signal was actually caused by long-term magnetic activity on the star itself, not by a real planet. Further studies confirmed this conclusion in the years that followed. The story of Peter van der Kamp remains one of the most famous controversies in modern astronomy. Starting in 1938, van der Kamp and his colleagues at the Sproul Observatory in Swarthmore College began painstakingly studying tiny changes in the position of Barnard's star on photographic plates. They searched for shifts as small as 1 micrometer, which might indicate the gravitational pull of an orbiting planet. At times, as many as 10 people worked together, averaging their results to reduce errors. In 1969, Van der Kamp published a paper suggesting a planet with a mass of about 1.6 times that of Jupiter, orbiting at a distance of 4.4 astronomical units. Later the same year, he refined his claim further, suggesting not one planet but two, with masses of about 1.1 and 0.8 times that of Jupiter. But other astronomers could not confirm his findings. In 1973, George Gatewood and Heinrich Eichhorn, using newer instruments at a different observatory, failed to detect any such planets. Earlier that same year, John L. Hershey, working at the very same Swarthmore Observatory, found that the supposed planetary signals actually lined up with times when the telescope's lens had been adjusted or repaired. What Van der Kamp had detected was not a planet at all, but an artifact of telescope maintenance. Despite mounting evidence against his claims, Van der Kamp never admitted error, and he continued publishing papers suggesting two planets around Barnard's star as late as 1982. He passed away in 1995. His successor at Swarthmore, Wolf Heinz, who specialised in double stars, openly criticised Van der Kamp's work from 1976 onwards, and the two men became estranged. The decades following Van der Kamp's disproven claims saw astronomers place tighter and tighter limits on what kinds of planets could still be hiding around Barnard's star. For example, in 1995, George Gatewood showed that planets with masses greater than 10 times that of Jupiter were impossible around the star. In 1999, interferometric observations with the Hubble Space Telescope ruled out planets larger than 0.8 Jupiter masses with orbits shorter than 1,000 days. In 2003, further work excluded Earth-like planets in the star's habitable zone if they had masses greater than 7.5 times that of Earth, or more than 3.1 times the mass of Neptune. In 2013, a new study combined 25 years of radial velocity data from the Lick and Keck observatories. By using advanced statistical methods, astronomers ruled out planets above 2 Earth masses with orbits shorter than 10 days, as well as planets larger than 10 Earth masses with orbits up to about 2 years long. The study also suggested that Barnard's star's habitable zone is very likely empty of Earth-sized or larger planets, except in special orbital configurations. Although these findings made the chances of discovering an Earth twin around Barnard's star smaller, the possibility was never completely ruled out, especially for small rocky planets that are much harder to detect. Missions such as NASA's planned Space Interferometry mission and the European Space Agency's Darwin mission had once chosen Barnard's star as a promising target, but both projects were eventually cancelled, Darwin in 2007 and SIM in 2010. By the time of the confirmed discoveries in the years 2024 and 2025, scientists had finally moved beyond decades of uncertainty. Instead of rumours, hints, and refuted claims, they now had real planets, small rocky worlds orbiting one of the closest stars to the Sun. The story of Barnard's star, filled with false starts, passionate debates, and decades of persistence, shows just how hard it is to detect other worlds and how rewarding it is when the truth at last comes to light. In the year 1998, astronomers made an unexpected discovery while observing Barnard's star. On the 17th day of July, during a study that was not even focused on stellar activity, but instead on measuring tiny changes in the star's motion across the sky, they noticed a sudden flare bursting from the star. This flare was detected through unusual changes in its spectral emissions. At first, the observation was puzzling, and it took 4 more years before scientists were able to fully analyse the event. When the results were finally published, they revealed that the flare had reached a temperature of around 8,000 kelvins, more than twice the usual surface temperature of Barnard's star. One of the researchers, Diane Paulson, remarked that this made the star an exciting object for amateur astronomers to watch, precisely because such events are unpredictable. What surprised scientists most was that Barnard's star is extremely old, and stars of such age are not usually expected to show strong bursts of activity. Stellar flares are still not completely understood, but they are thought to be caused by powerful magnetic fields. These fields disrupt the normal flow of hot plasma inside a star, and sometimes release their energy all at once in the form of an explosive flare. Strong magnetic fields usually exist in stars that spin quickly, because rapid rotation helps to sustain them. Old stars, on the other hand, rotate very slowly and therefore are much less likely to produce violent flares. For Barnard's star, an ancient red dwarf, to unleash such a powerful event seemed highly unusual and rare. Studies of the star's periodic activity also suggested that it should remain quiet. Research carried out in 1998 looked for regular changes in its brightness over time and found almost nothing, only the faintest hint of a single dark star spot over a span of 130 days. This reinforced the idea that Barnard's star should not be very active, making the flare all the more remarkable. Despite its rarity, this kind of stellar activity has drawn great scientific interest. Astronomers hope that by studying Barnard's star closely, they can use it as a model for understanding the countless other old red dwarfs scattered throughout the galaxy. Modern studies focus on measuring its emissions in both X-rays and ultraviolet light, since these can reveal more about how such stars behave. This has direct importance for astrobiology. The zones around red dwarfs where planets could potentially support life are located very close to the star itself. Any planet in such a zone would be directly exposed to powerful solar flares, intense stellar winds, and violent ejections of plasma. All of these could strongly affect the chances for life to exist. Years later, in the year 2019, scientists observed even more activity. 2 separate ultraviolet flares were detected, each carrying energy of about 3 × 10 to the power of 22 joules, along with a single X-ray flare releasing 1.6 × 10 to the power of 22 joules. These are enormous amounts of energy by any measure. Calculations suggest that if such activity continues, the radiation and particles from Barnard's star could strip away planetary atmospheres over time. In fact, the estimated rate of loss for the planet known as Barnard's star B could equal around 87 Earth-like atmospheres in 1 billion years through heating processes, and about 3 Earth-like atmospheres in 1 billion years through ion escape processes. Barnard's star also has a very familiar neighbourhood in space. Like the Sun, it is surrounded mostly by small red dwarf stars, which are the most common stars in the Milky Way. Its closest stellar neighbour at present is another red dwarf called Ross 154, which lies about 1.66 parsecs away, that is, roughly 5.5 light-years. The Sun itself is the next nearest system at just under 6 light-years, while Alpha Centauri is a little farther away at about 6.5 light-years. If you were standing near Barnard's star and looked up at the sky, the Sun would appear on the exact opposite side of the heavens, positioned in the faint constellation of Monoceros. Seen from that distance, the Sun would shine as brightly as the star Pollux does in our own night sky. Barnard's star has also played a role in human imagination about space travel. It was chosen as one of the targets for Project Daedalus, a bold scientific study carried out between the years 1973 and 1978. The goal of this project was to examine whether humanity, using advanced but still conceivable technology, could send an uncrewed spacecraft to another star system within a single human lifetime. Barnard's star was selected partly because many scientists at the time suspected it might have planets orbiting it. The proposed design of the spacecraft was extraordinary. It would be a nuclear pulse rocket using nuclear fusion, specifically the bombardment of deuterium and helium, 3 atoms with electrons, to produce energy. By accelerating continuously for 4 years, such a ship could reach about 12% of the speed of light. At that velocity, it could cross the distance to Barnard's star in only 50 years. Once there, it would not only study the star and any planets, but also analyse the interstellar medium, the thin gas and dust between stars, and establish precise astronomical reference points for future missions. The excitement did not stop there. In the year 1980, a researcher named Robert Freitas proposed an even more ambitious vision. He imagined building a self-replicating spacecraft, launched from orbit around Jupiter, that could travel to Barnard's star in just 47 years. Once it arrived, it would construct an automated factory capable of producing probes and eventually even building a full copy of itself. Over the course of 1,000 years, this process of self-replication could, in theory, allow an expanding wave of robotic explorers to spread outward through the galaxy, searching for and potentially making contact with extraterrestrial civilizations. Sirius is the brightest star in the entire night sky. outshining every other star that humans can see with the naked eye. Astronomers officially call the star Alpha Canis Majoris, which means the brightest star in the constellation of Canis Major, the Greater Dog. For short, it is often written as Alpha Siema. With a visual magnitude of -1.46, Sirius shines almost twice as brightly as Canopus, the second brightest star in the heavens. Sirius is not just one star, but actually a binary system, two stars orbiting around each other. The larger and brighter one is Sirius A, a hot white star of spectral type A0 or A1. Its companion is much smaller and dimmer, a dense white dwarf star called Sirius B of type Da2. The two stars swing around each other once every 50 years, and the distance between them changes, sometimes as close as about 8 astronomical units, and sometimes as far as 31 astronomical units. The reason Sirius looks so dazzling is because it is both truly luminous on its own, and also very close to us compared to most other stars. It lies at a distance of about 2.64 parsecs, which is about 8.5 light-years away, making it one of the nearest stellar neighbours of Earth. Sirius is moving gradually closer to our solar system, which means it will shine even a little brighter in the far future. Around 60,000 years from now, it will reach its peak brightness of magnitude -1.68. Strangely enough, at about that same time, Sirius will also become the southern pole star, because the slow wobble of Earth's axis, known as axial precession, will cause it to align closely with the southern celestial pole around the year 66,270 of our calendar. At that moment, Sirius will come within about 1.5 degrees of the pole. After that era, the star will slowly move away, fade a little, but will still remain the brightest star in the night sky for about the next 210,000 years, until Vega, an even more powerful star, takes over as the brightest. Sirius A has roughly twice the mass of our Sun, and shines with an absolute magnitude of +1.43. It radiates about 25 times more light than the Sun, though it is still less brilliant than other giants such as Canopus, Betelgeuse, or Rigel. The Sirius system is relatively young in cosmic terms, only about 200 to 300 million years old. At first, both stars were hot and blue, but the heavier one, which became Sirius B, burned its fuel more quickly. It expanded into a red giant, shed its outer layers, and about 120 million years ago collapsed into the dense white dwarf we see today. People have given Sirius countless names across cultures and eras. It is often called the Dog Star because of its place in Canis Major, the Great Dog constellation. In ancient Egypt, the rising of Sirius just before sunrise signalled the yearly flooding of the Nile, which brought fertility to the land. For the ancient Greeks, its appearance marked the arrival of the hottest days of summer, known as the Dog Days. For the Polynesians of the southern hemisphere, Sirius marked the time of winter, and was a crucial guide for navigation across the vast Pacific Ocean. The very name, Sirius, passed from Greek into Latin and was already in use by the 7th century before Christ, when the poet Hesiod mentioned it in his work Works and Days. Some scholars believe the name may have an even older origin, possibly linked to the Egyptian god Osiris. In the modern era, in the year 2016, the International Astronomical Union officially confirmed Sirius as the star's proper name in its standardized catalogue. But Sirius has not been known by only one name. Across history and across the world, it has gathered more than 50 other titles. In medieval Europe, Geoffrey Chaucer referred to it as Alhabor, and it often appeared on astrolabes as the head of a dog. In India, Sanskrit texts call it Mrgavyada, meaning deer hunter, or Lubdaka, the hunter. In this tradition, the star is linked with the god Rudra, who later came to be identified with Shiva. In the Malayalam language of southern India, Sirius is called Makarajyoti, and it plays a role in religious ceremonies at the pilgrimage site of Sabarimala. In Scandinavia, it was called Lokabrena, meaning Loki's torch, or burning dun by Loki. In medieval astrology, it was classified as one of the Bohemian fixed stars and was associated with precious stones and plants such as beryl and juniper. In ancient Egypt, Sirius was worshipped as the goddess Sopdet, or Sothis in Greek, who was seen as the guarantor of life and fertility. Sopdet was linked with the constellation of Orion, personified as the god Sar, her husband. Together they were believed to have a son, Sopdu, a sky god. Later, Sopdet was connected with the goddess Isis, while Sar was associated with Osiris. The 70-day period when Sirius disappeared from the night sky each year was seen as the journey of Isis Sopdet and Osiris Sar through the underworld. The Greeks thought of Sirius as a star of fire and danger. When it rose before the sun, they believed it caused the scorching summer heat, making crops wither and even influencing human behaviour. They described its light as burning or flaming, and anyone harmed by its supposed powers was said to be starstruck. On the island of Chios, people offered sacrifices to Sirius and to Zeus in hopes of receiving cooling winds. If Sirius rose clear and bright, it was seen as a sign of good fortune. If it was faint or hazy, it was feared to bring disease. Coins from the 3rd century before Christ found on the island show dogs and stars with shining rays, reflecting the importance of Sirius in their culture. The Romans also gave the star great significance. Each year, around the 25th of April, they marked the heliacal setting of Sirius by sacrificing a dog, along with wine, incense and a sheep, to the goddess Robigo, praying that Sirius would not bring disease to their wheat harvest. For the Polynesians, Sirius was one of the most important guides for long-distance ocean travel. Its position in the sky matched the latitude of the Fiji Islands, meaning it passed directly overhead each night. They imagined Sirius as part of a great celestial bird, with Canopus as one wingtip and Procyon as the other. To the Maori of New Zealand, Sirius was called Takurua and signalled the arrival of winter. In Hawaii, it was celebrated as Kaulua, the Queen of Heaven. Other names are found across the Pacific: Taua in the Marquesas, Rehua in New Zealand, and long ceremonial names in Tahiti, such as Taurua Faupapa, Festival of the Ancient Chiefs, and Taurua e Hiti te Taratewhai, festival that rises with prayers and sacred rites. Thus, Sirius is far more than just a bright point of light in the sky. It has been a guide for sailors, a marker of seasons, a signal of life-giving floods, an object of worship, and a symbol of both blessing and danger. For thousands of years, it has inspired awe, stories, rituals, and traditions across nearly every part of the world. In the year 1717, the English astronomer Edmund Halley made a discovery that changed the way people thought about the stars. For centuries, most scholars had believed that the stars were fixed in the sky, unchanging in their positions except for the slow daily and yearly movements caused by the Earth. Halley challenged this belief when he carefully compared modern measurements of star positions with those recorded almost 1600 years earlier by the ancient Greek-Egyptian astronomer Claudius Ptolemy in his great work, the Almagest, written in the 2nd century after Christ. Halley noticed that several bright stars had moved slightly across the sky over this long period of time. Most stars appeared to stay in place, but not all of them. He pointed out that Aldebaran, Arcturus and Sirius had shifted quite noticeably. Sirius, the brightest star in the night sky, had moved about 30 arc-minutes to the southwest, roughly the same apparent width as the full moon. This was the first clear demonstration of what is now called proper motion, the real movement of stars through space over time as seen from Earth. In the year 1868, another breakthrough involving Sirius was made. It became the very first star to have its motion toward or away from the Earth measured, a field of study now called radial velocity. The English astronomer Sir William Huggins observed the spectrum of Sirius, the rainbow-like band of light that reveals details about a star's nature. He noticed that the spectral lines were shifted slightly toward the red, a phenomenon known as redshift. From this, Huggins concluded that Sirius was moving away from the solar system at a speed of about 40 kilometers per second. Later, more accurate studies showed that his estimate was too high, and more importantly, in the wrong direction. Modern measurements reveal that Sirius is actually approaching the Sun at a speed of about 5.5 kilometers per second. The negative sign in the modern data indicates approach, while a positive value would indicate recession. Long before these discoveries, in the year 1698, the Dutch scientist Christian Huygens attempted to estimate the distance to Sirius. In his book Cosmotheoros, he guessed that Sirius was about 27,664 times farther from the Earth than the Earth is from the Sun. In modern terms, this would equal less than half a light year, specifically about 0.437 light years. His estimate was far too small, but it represented an early attempt to measure the unimaginably vast distances to the stars. Throughout the 18th and early 19th centuries, many astronomers tried to measure the parallax of Sirius, the tiny apparent shift in a star's position, against the background of more distant stars, caused by the Earth moving around the Sun. Jacques Cassini, Neville Maskelyne, and Giuseppe Piazzi all attempted such measurements, but none were accurate. Even the great Friedrich Bessel failed to detect a reliable parallax for Sirius. It was only in the early 1800s that more progress was made. The Scottish astronomer Thomas Henderson, working with observations from South Africa in the years 1832 to 1833, and later combined with further observations by Thomas Maclair in the years 1836 to 1837, proposed that Sirius had a parallax of about 0.23 arc-seconds. In 1839, Henderson concluded that the true value must be less than half an arc-second. For most of the 19th century, astronomers accepted a value of about 1/4 of an arc-second. Modern measurements now show the actual parallax to be close to 0.4 arc-seconds. The Hipparcos satellite, launched in the late 20th century, gave a highly precise parallax for Sirius, corresponding to a distance of 8.6 light-years, with an uncertainty of only 0.04 of a light-year. The white dwarf companion Sirius B is assumed to lie at the same distance. Data from the more advanced Gaia satellite, published in its third data release, gave an even more precise figure of about 8.709 light-years for Sirius B, with a margin of error of only 0.005 of a light-year. However, this value has been flagged as possibly unreliable due to excess noise in the measurements. In the 19th century, further surprises awaited astronomers. On the 10th of August, 1844, the German astronomer Friedrich Wilhelm Bessel wrote a letter proposing that Sirius had an invisible companion, based on irregularities in its motion across the sky. His prediction came true on the 31st of January 1862, when the American telescope maker Alvin Graham Clark first saw the faint star that would later be known as Sirius B. He discovered it while testing a new giant telescope lens, an 18.5-inch refractor built for the Dearborn Observatory. At the time, it was the largest telescope in the United States, and one of the largest in the world. The discovery was confirmed only a few weeks later, on the 8th of March, with smaller telescopes. From then on, the main star has been referred to as Sirius A, while its faint companion is called Sirius B. Since the year 1894, astronomers have occasionally reported strange irregularities in the orbit of Sirius A and B, leading some to suspect the presence of a third, much smaller companion star. The data best fits the idea of a 6-year orbiting body with about 6% of the Sun's mass, but if it exists, it would be much fainter than Sirius B. So faint that even the most advanced observations have failed to confirm it. In fact, in the year 2008, new studies showed no evidence of a third star or a planet in the system. An object once reported in the 1920s as a possible third star is now known to have been just a background star. In the year 1915, the American astronomer Walter Sidney Adams, using a 60-inch telescope at Mount Wilson Observatory, studied the spectrum of Sirius B. He showed that the faint star was extremely hot and white in colour. Astronomers realised that this was a new type of object, later called a white dwarf. Sirius B became only the second white dwarf ever identified. Decades later, in 1959, Robert Hanbury Brown and Richard Twiss, working at Jodrell Bank, used a new technique called stellar intensity interferometry to measure the diameter of Sirius A for the first time. Finally, in the year 2005, observations with the Hubble Space Telescope showed that Sirius B is nearly the same size as the Earth, about 12,000 kilometers across, but with a mass slightly greater than that of the Sun. Around the year 150 of the Common Era, Claudius Ptolemy, an ethnic Greek-Egyptian astronomer living during the Roman period in Alexandria, undertook one of the most ambitious star-mapping projects of the ancient world. In the 7th and 8th books of his famous work, the Almagest, Ptolemy carefully charted the positions of hundreds of stars. He placed Sirius, the brightest star in the night sky, along the central meridian of his celestial globe. Ptolemy described Sirius as having a reddish hue, a characteristic he shared with 5 other notable stars: Betelgeuse, Antares, Aldebaran, Arcturus, and Pollux. Modern observations confirm that these stars do indeed appear orange or red to the human eye. The first person to notice the discrepancy between Ptolemy's description of Sirius as red and its modern white appearance was Thomas Barker, an amateur astronomer and squire of Linden Hall in Rutland. In the year 1760, Barker presented a paper on the subject to a meeting of the Royal Society in London. Over time, the idea gained further attention as astronomers observed other stars that change in brightness, leading to the suggestion that stars might also change in colour. Sir John Herschel noted this possibility in 1839, likely influenced by his observation of Eta Carinae 2 years earlier. The topic of red Sirius was revived decades later by Thomas J.J.C., who published several papers on the subject beginning in 1892 and presented a final summary in 1926. C cited not only Ptolemy, but also classical authors such as the poet Aratus, the orator Cicero, and the Roman general Germanicus, all of whom described Sirius as red. He did, however, acknowledge that Cicero and Germanicus were not astronomers and had merely translated Aratus's poem Phenomena. Even the philosopher Seneca referred to Sirius as being a deeper red than the planet Mars, although it is possible that these descriptions were poetic ways of signalling bad omens rather than literal observations of the star's colour. In 1985, German astronomers Wolfhard Schlosser and Werner Bergmann brought attention to an 8th century Lombardic manuscript containing De Cursu Stellarum Ratio, a text by St. Gregory of Tours. The manuscript taught readers how to calculate the times for nighttime prayers based on the positions of stars, and it referred to a bright star called Rubeola, meaning reddish, which the authors proposed might be Sirius. They suggested this as evidence that Sirius B, the faint companion of Sirius, could have been a red giant at that time. Other scholars, however, argued that St. Gregory was more likely referring to Arcturus rather than Sirius. Interestingly, not all ancient observers described Sirius as red. The 1st century poet Marcus Manilius called it sea blue, and the 4th century poet Aviennius agreed. In China, historical records consistently reported Sirius as a white star. A careful re-examination of Chinese texts from the 2nd century before the Common Era through the 7th century of the Common Era confirmed that reliable Chinese sources always describe Sirius as white. Despite these differences, the number of historical accounts referring to Sirius as red was significant enough to prompt researchers to consider physical explanations. These theories are generally divided into two types: intrinsic and extrinsic. Intrinsic theories suggest that Sirius itself underwent a real change in its physical properties over the past 2,000 years. The most discussed version of this idea proposes that Sirius B, now a white dwarf, was once a red giant. Extrinsic theories, on the other hand, suggest that the apparent redness of Sirius could be caused by something between the star and the observer, such as interstellar dust or effects within Earth's atmosphere. Most intrinsic explanations have been rejected. The evolution of either Sirius A or Sirius B is too slow to produce such dramatic changes over just 2,000 years, and there is no visible nebulosity or other evidence to suggest that such a transformation occurred. The possibility of a third star altering Sirius's colour is also inconsistent with observations. Similarly, extrinsic theories involving interstellar dust clouds are unlikely. While a passing cloud could redden Sirius, the effect would also dim the star so much that it would appear faint, making the colour difficult to perceive with the naked eye, something historical observers never reported. The most plausible explanations involve Earth's atmosphere. Atmospheric turbulence can cause scintillations, creating rapid, brief shifts in a star's apparent colour, though not necessarily red. More systematic reddening occurs when sunlight or starlight passes through particles in the atmosphere, just like the sun appears red at sunrise or sunset. In the case of Sirius, this effect could make the star appear reddish without dimming it noticeably. Cultural practices likely amplified this effect. In many Mediterranean societies, the heliacal rising and setting of Sirius, that is, its first appearance in the morning sky or its last visible setting at night, was considered astrologically significant. Observers would often watch Sirius close to the horizon, where atmospheric reddening is strongest, and record its appearance. In contrast, Chinese astronomers, who did not follow this tradition, consistently described Sirius as white, likely observing it higher in the sky. Sirius shines as the brightest star in the entire night sky, with an apparent magnitude of -1.46, making it nearly twice as luminous as the second brightest star, Canopus. Despite this brilliance, when viewed from Earth, Sirius appears dimmer than the planets Jupiter and Venus, and at certain times it can also be fainter than Mercury and Mars. The star can be seen from nearly every corner of the planet, with the exception of regions north of 73 degrees latitude, where it remains perpetually below the horizon. In some northern cities, such as St. Petersburg, Sirius barely climbs above the horizon, reaching only 13 degrees in the sky. Its position in the heavens, at a declination of roughly minus 17 degrees, makes it a circumpolar star for observers south of 73 degrees south latitude, meaning it never sets and can be seen at all hours of the night. From the southern hemisphere during the early days of July, Sirius is especially striking, appearing both in the evening sky after sunset and again in the morning before sunrise. For observers in the northern hemisphere, Sirius joins Procyon and Betelgeuse to form one of the 3 points of the famous winter triangle. Under ideal conditions, Sirius can even be spotted in broad daylight with the naked eye. The perfect viewing requires a clear sky, high elevation, the star passing directly overhead, and the sun positioned low on the horizon. These conditions are most often met around sunset in the months of March and April, and around sunrise in September and October. Observing Sirius is generally easier from the southern hemisphere because of its southern declination. Sirius is not a lone star but a binary system, meaning it consists of 2 stars orbiting each other. The distance between them changes from a minimum of 3 arcseconds to a maximum of 11 arcseconds. When they are closest, observing Sirius B, the fainter companion, is extremely difficult and requires a telescope with at least a 300mm or 12-inch aperture and exceptionally stable atmospheric conditions. The pair last reached their closest point, or periastron, in 1994, after which they gradually moved apart, making the 2 stars easier to distinguish through a telescope. Their farthest point, or apostron, occurred in 2019, but from Earth, the maximum apparent separation was observed in 2023, measuring 11.333 arcseconds. Located at a distance of 2.6 parsecs, approximately 8.6 light-years, Sirius is among the 8 nearest stars to the Sun and ranks as the 5th closest stellar system to us. Its closeness explains why it appears so bright in our night sky, similar to other nearby stars such as Alpha Centauri, Procyon and Vega, and unlike more distant intrinsically luminous giants like Canopus, Rigel, or Betelgeuse, Sirius shines about 25 times more brightly than the Sun. Its nearest large stellar neighbour is Procyon, which lies about 1.61 parsecs, or 5.24 light-years, away. The Voyager 2 spacecraft, launched in 1977 to explore the giant planets of our solar system, is expected to pass within 4.3 light-years, or 1.3 parsecs, of Sirius in roughly 296,000 years. Sirius A, the primary star in the system, is a main sequence star of early A spectral type, with a surface temperature around 9,940 kelvins and a mass of about 2.063 times that of the Sun. Its companion, Sirius B, is a dense white dwarf that has already exhausted its main sequence life. Though Sirius B is currently 10,000 times less bright than its partner in visible light, it was originally the more massive of the 2 stars. The Sirius system is estimated to be about 230 million years old. In its earliest days, the system likely consisted of 2 bluish-white stars orbiting each other every 9.1 years in a more elliptical path. The system emits slightly more infrared radiation than expected, suggesting the presence of dust, somewhat unusual for a binary star system. X-ray observations from the Chandra Observatory reveal that Sirius B actually outshines Sirius A as a source of X-rays. Observational studies conducted in 2015 using the Very Large Telescope Survey have searched for additional companions around Sirius. These studies ruled out the presence of giant planets more than 11 times the mass of Jupiter, at a distance of half an astronomical unit from Sirius A, 6 to 7 times the mass of Jupiter at 1 to 2 astronomical units, and down to around 4 times the mass of Jupiter at 10 astronomical units. No planets were detected around Sirius B either. Sirius A, also known as the dog star, rotates relatively slowly at 16 kilometers per second, causing minimal flattening at its equator, unlike the faster spinning star Vega, which rotates at 274 kilometers per second and bulges significantly. Sirius A also possesses a weak magnetic field on its surface. Formed from a collapsing molecular cloud, the star began generating energy through nuclear fusion about 10 million years after its birth, using the CNO cycle at its convective core. Scientists predict that within roughly 1 billion years, Sirius A will exhaust the hydrogen in its core, expand into a red giant, and eventually shrink to become a white dwarf. Sirius A is classified as an AM star, meaning its spectrum shows unusually strong absorption lines of metals, including iron. Its spectral type is sometimes given as a 0 MEA1 VA, indicating slight differences depending on whether hydrogen and helium lines or metallic lines are considered. Compared with the Sun, Sirius A contains about 316% of the Sun's iron in its atmosphere, though this enrichment is likely limited to the star's surface layers due to radiative levitation of heavier elements. Sirius B, often affectionately called the Pup, is one of the most massive white dwarfs known, with a mass slightly over 1 solar mass, compressed into a volume roughly equal to that of Earth. Its surface temperature reaches 25,200 kelvins, but lacking internal heat sources, it will slowly cool over the next 2 billion years. Sirius B became a white dwarf around 120 million years ago, after evolving off the main sequence and passing through a red giant phase. Its original mass was approximately 5 times that of the Sun, and it shone between 600 and 1200 times more brightly. During its giant stage, it may have contributed heavy elements to Sirius A, explaining the high metallicity observed today. Composed primarily of carbon and oxygen from helium fusion in its earlier life, Sirius B is enveloped by lighter elements, with gravity causing a layered structure. Its outer atmosphere now consists almost entirely of hydrogen, and no other elements are observed in its spectrum. Although the Sirius system resembles binaries that could, under the right circumstances, produce type A supernovae, the stars are too far apart for this to happen. Novae events, however, remain a possibility. Since the year 1894, astronomers have noticed hints of strange irregular behaviour in the orbits of Sirius A and its companion Sirius B. These irregularities seem to follow a rough cycle of about 6 to 6.5 years. Nearly a century later, in 1995, a detailed study suggested that there might be a hidden companion in the system, a small, dim object with a mass roughly 5% that of our Sun. This mysterious companion could be a tiny red dwarf, or a relatively large brown dwarf, shining so faintly that its apparent brightness would be more than 15th magnitude, and it would lie less than 3 arcseconds away from Sirius A, making it extremely difficult to spot. However, in 2017, the Hubble Space Telescope conducted more precise measurements of the Sirius system. These observations definitively ruled out the existence of a companion as large as a typical star, sometimes referred to as Sirius C. At the same time, the data still left room for a smaller substellar object, such as a low-mass brown dwarf. The 1995 study had predicted that such a companion would cause Sirius A to shift slightly in the sky by around 90 milliseconds, about 0.09 arcseconds. Yet Hubble found no such displacement, measuring positions with an astonishing precision of 5 milliseconds, 0.005 arcseconds. From this, astronomers concluded that there could be no object orbiting Sirius A with more than about 3.33% of the Sun's mass, roughly 35 times the mass of Jupiter, within half a year, or more than 1.4% of the Sun's mass, about 15 Jupiter masses, within 2 years. Similarly, any companion to Sirius B would have to be smaller than about 2.5% of the Sun's mass, 25 Jupiter masses, if orbiting in half a year, or smaller than roughly 1% of the Sun's mass, 10 Jupiter masses, if orbiting in 1 year and 10 months. In short, the Sirius system almost certainly contains no additional bodies larger than a small brown dwarf or a massive exoplanet. Going back over a century, in 1909, Danish astronomer Einar Hertzsprung was the first to propose that Sirius might belong to a larger group of stars moving together through space, known today as the Ursa Major Moving Group. This group consists of about 220 stars that share a common motion, suggesting they may have formed together. Originally, they were part of an open star cluster, but over time they drifted apart, no longer bound by gravity. Later studies in 2003 and 2005 raised doubts about Sirius's membership in this group. The Ursa Major group is estimated to be roughly 500 million years old, give or take 100 million years, while Sirius appears to be only about half that age, with a chemical composition similar to the Sun's, making it too young to truly belong. Astronomers now think Sirius may instead be part of a larger, more loosely connected association known as the Sirius supercluster. This grouping would include other scattered stars such as Beta Aurigae, Alpha Coronae Borealis, Beta Crateris, Beta Eridani, and Beta Serpentis. The Sirius supercluster is one of 3 significant clusters of stars located within 500 light-years, about 150 parsecs of the Sun. The other 2 well-known clusters are the Hyades and the Pleiades, each containing hundreds of stars. In an intriguing discovery in 2017, astronomers found a massive star cluster just 10 arc-minutes away from Sirius when seen from Earth, making the 2 appear very close in the night sky. This cluster was uncovered through a careful statistical analysis of data from the Gaia Space Observatory. Although it lies over 1,000 times farther away than the Sirius system itself, its immense size allows it to shine at an apparent magnitude of 8.3, bright enough to be seen with small telescopes or binoculars. Orion is one of the most famous and easily recognizable groups of stars in the night sky, especially during winter in the Northern Hemisphere. It is part of the 88 modern constellations recognized today, and it was also one of the 48 constellations described by the ancient astronomer Ptolemy in the 2nd century. The constellation is named after Orion, a mighty hunter from Greek mythology, who is said to roam the heavens with his belt and sword. Orion is most striking in the winter months of the Northern Hemisphere, when 5 other nearby constellations join it to form the winter hexagon, a large star pattern visible across the sky. The constellation's 2 brightest stars, Rigel and Betelgeuse, are among the brightest stars in the night sky. Both are enormous supergiant stars, each with slight changes in brightness over time. Orion also has 6 other stars brighter than magnitude 3, including the 3 stars that make up the famous straight line known as Orion's belt. In addition to its bright stars, Orion is home to several spectacular celestial sights. The Orion Nebula, one of the brightest clouds of gas and dust in the sky, lies along the Hunter's Sword. Every year, Orion is also the radiant point for the Orionids, one of the strongest meteor showers, which originates from fragments of Halley's Comet. Orion shares its borders with several other constellations. To the northwest lies Taurus, to the southwest Eridanus, to the south Lepus, to the east Monoceros, and to the northeast Gemini. Covering nearly 600 square degrees, Orion is the 26th largest constellation in the sky. The exact borders of the constellation were drawn in 1930 by the Belgian astronomer Eugène Delporte, forming a polygon of 26 sides. In the equatorial coordinate system used by astronomers, Orion spans from 4 hours 43 minutes and 18 seconds to 6 hours, 25 minutes and 30 seconds in right ascension, and from 22.87 degrees to negative 10.97 degrees in declination. The International Astronomical Union gave Orion the 3-letter abbreviation ORI in 1922. Orion is easiest to see in the evening sky from January to April, which corresponds to winter in the Northern Hemisphere and summer in the Southern Hemisphere. Near the equator, within about 8 degrees north or south, Orion passes directly overhead, making it particularly striking for observers in places like Kenya, Indonesia, Colombia, and Ecuador. During December, Orion appears almost at the zenith around midnight, while in February it shines in the evening sky. From May to July, Orion is hidden in the daytime sky for most of the world, making it invisible to casual observers. However, in Antarctica during the southern hemisphere's winter, the sun stays below the horizon even at midday. This means that only the brightest stars of Orion can sometimes be seen near local noon, low in the northern sky where the sun is just below the horizon. At the South Pole itself, Rigel appears only 8 degrees above the horizon, and Orion's belt sweeps across the sky nearby. During the southern hemisphere's summer months, Orion is not visible in Antarctica at all, because the sun never sets south of the Antarctic Circle at that time. Orion is not just beautiful, it is also very useful for finding other stars. By extending a line through the three belt stars to the southeast, observers can find Sirius, the brightest star in the night sky. Extending the line northwest points to Aldebaran in Taurus. A line drawn east across Orion's shoulders leads to Procyon in Canis Minor. Another line from Rigel through Betelgeuse points to the twin stars Castor and Pollux in Gemini. Rigel also belongs to the Winter Circle, a larger pattern of bright stars, and Sirius and Procyon form points in both the Winter Triangle and the Winter Circle. Orion's 7 brightest stars create a distinctive hourglass shape in the sky. 4 stars, Rigel, Betelgeuse, Bellatrix and Scythe, form a large, rough rectangle. At the centre of this rectangle are the 3 belt stars, Alnitak, Alnilam and Mintaka. Above the rectangle is Orion's head, marked by the 8th star Mesa. Hanging down from the belt is Orion's sword, a smaller line of 3 stars, with the middle star actually being the Orion Nebula. Many of Orion's stars are massive, hot, and luminous blue supergiants, and the stars of the belt and sword are part of a group known as the Orion OB1 Association. Betelgeuse, with its distinctive red colour, is also part of this group, though it may have been ejected from the cluster in the past. Betelgeuse, also called Alpha Orionis, is a huge red supergiant approaching the end of its life. It is Orion's right shoulder and the second brightest star in the constellation. Betelgeuse's brightness varies slightly, and it usually ranks around the 11th brightest star in the night sky, though it has fluctuated from 10th to 23rd in recent years. In the next 100,000 years, Betelgeuse is expected to explode as a supernova, possibly becoming so bright that it could be seen in daylight and outshine the moon. Rigel, or Beta Orionis, is a blue supergiant and forms Orion's left foot. It is the 7th brightest star in the night sky, and, like Betelgeuse, is fusing heavy elements in its core. Eventually Rigel will end its supergiant stage, either exploding as a supernova or shedding its outer layers to become a white dwarf. Bellatrix, known as Gamma Orionis, marks Orion's left shoulder. It is the 27th brightest star in the night sky and is a blue giant. Bellatrix is not massive enough to explode as a supernova, and its brightness comes mostly from its very high temperature. Its name means the female warrior, and it is sometimes called the Amazon star. Bellatrix is also the closest major star in Orion, at only 244.6 light-years from the solar system. The 3 stars of Orion's belt each have unique characteristics. Mintaka, or Delta Orionis, is the faintest of the 3 belt stars. Its name means the belt, and it is a multiple star system composed of a large blue giant and an even more massive O-type main sequence star. Mintaka is an eclipsing binary, meaning the brightness dips when one star passes in front of the other. Mintaka is the westernmost and northernmost star in the belt. Alnilam, or Epsilon Orionis, is the middle and brightest belt star. Its name means string of pearls in Arabic. Alnilam is a blue supergiant, and despite being almost twice as far from the Sun as the other belt stars, it shines nearly as brightly. It is also losing mass rapidly because of its enormous size, and it is the farthest major star in Orion, at 1,344 light-years away. Alnitak, or Zeta Orionis, is the easternmost belt star. Its name means the girdle, and it is a triple star system with a hot blue supergiant as its primary component, making it the brightest O-type star in the night sky. Scythe, or Kappa Orionis, marks Orion's right foot. It is similar in size and distance to Rigel, but it appears much fainter. Its name means the sword of the giant. Mesa, or Lambda Orionis, forms Orion's head. It is a multiple star system with a combined brightness of magnitude 3.33, and its name means the shining one. In every part of the sky, Orion is a dazzling constellation, offering not only a spectacular show of bright stars and stunning nebulae, but also a celestial map for locating other stars. Its mixture of massive blue supergiants, a giant red star, and a collection of bright, well-placed stars has made it one of the most important and beloved constellations in human history. Orion's belt, also called the Belt of Orion, is one of the most famous patterns of stars in the night sky. It is an asterism, which means a noticeable group of stars within a larger constellation. This striking belt is made up of 3 bright stars, Alnitak, Alnilam, and Mintaka. Alnitak, the easternmost star of the trio, is about 800 light-years away from Earth. It is incredibly bright, shining with the energy of roughly 100,000 suns, although much of this energy is in ultraviolet light, which our eyes cannot see. Alnitak has an apparent brightness, or magnitude, of 1.8, making it easily visible to the naked eye on a clear night. In the middle of the belt sits Alnilam, located approximately 2,000 light-years from Earth. It shines with a magnitude of 1.7 and emits ultraviolet light, about 375,000 times more powerful than the Sun. Mintaka, the westernmost star, is around 915 light-years away. It shines with a magnitude of 2.21 and is about 90,000 times brighter than our Sun. Interestingly, Mintaka is a double star, with its two components orbiting each other every 5.73 days. In the northern hemisphere, Orion's belt is at its most dazzling in the night sky during January, around 9 o'clock in the evening, when it reaches the highest point along the local meridian. Southwest of Alnitak lies Sigma Orionis, a remarkable multiple star system made up of 5 stars. Together they shine with an apparent magnitude of 3.7 and are located roughly 1,150 light-years away. To the southwest of Mintaka is another multiple star system, Eta Orionis, which is made up of 4 stars. Hanging below Orion's belt is his famous sword. This sword contains several fascinating objects: the Orion Nebula, the Messier 43 Nebula, Sh2279, also called the Running Man Nebula, and bright stars such as Theta Orionis, Iota Orionis, and 42 Orionis. Orion's head is marked by a small triangle of stars. The top point of the triangle is Mesa, a hot blue giant star of spectral type 083, shining with a magnitude of 3.54. Mesa is roughly 1,100 light-years from Earth. The base of the triangle is formed by the stars Phi 1 and Phi 2 Orionis. Nearby lies the young and variable star Fu Orionis, known for its occasional bursts of brightness. Stretching north from Betelgeuse, the stars form Orion's club. The star Mu Orionis marks the elbow, Nu and Xi Orionis form the handle, and Chi 1 and Chi 2 Orionis mark the tip of the club. Just east of Chi 1 lies the red giant star U Orionis, a mirror-type variable that brightens and dims over time. West of Bellatrix, 6 stars named Pi Orionis, Pi 1, Pi 2, Pi 3, Pi 4, Pi 5, and Pi 6 Orionis create Orion's shield. Each year, around the 20th of October, the Orionid meteor shower reaches its peak. The meteors appear to come from the border between Orion and the constellation Gemini. On a dark night, viewers can see as many as 20 meteors per hour. This meteor shower originates from Halley's Comet. The Orion Nebula, also called Messier 42, is one of the most spectacular objects in Orion's sword. Within it lies the Trapezium cluster, made up of 4 bright stars forming a trapezoid, as well as dozens of newborn stars and several brown dwarfs. The cluster is about 1,500 light-years away. The main stars in the trapezium are only a few 100,000 years old and shine at extreme temperatures, some reaching 60,000 kelvins. Using binoculars or a telescope, observers can see the glowing gas, dust clouds, and regions where new stars are still forming. Another beautiful nebula in Orion is Messier 78, also called NGC 2068. It has a brightness of 8.0 and is about 1,600 light-years from Earth, making it slightly dimmer than the Orion Nebula. In a telescope, it can be mistaken for a comet. Messier 78 is associated with the variable star VEM 351 Orionis, whose brightness changes quickly over short periods. Nearby is NGC 1999, another bright nebula with a magnitude of 10.5, located about 1,500 light-years away. The young variable star V380 Orionis is embedded within it. Close to Alnitak is IC 434, the famous Horsehead Nebula. Its dark shape, resembling a horse's head, stands out against the glowing gas behind it. NGC 2174 is an emission nebula located about 6,400 light-years from Earth, glowing with the light of newly forming stars. Even a small telescope reveals many wonders in Orion, multiple stars like Iota Orionis and Sigma Orionis, and nebulae such as M43 and M78. A larger telescope can uncover even fainter and more distant objects such as the Flame Nebula NGC 2024 and smaller star clusters. On very dark nights, or with long exposure photography, one may glimpse Barnard's Loop, a giant arc of glowing gas surrounding much of the constellation. All these nebulae and star-forming regions belong to the larger Orion molecular cloud complex, a vast region of gas and dust located about 1,500 light-years from Earth and stretching across hundreds of light-years. It is one of the most active and visually stunning regions of star formation in the entire Milky Way galaxy. UY Scuti, also catalogued as BD-12 degrees 5055, is a massive red supergiant star situated roughly 5,900 light-years away from Earth in the constellation Scutum. A red supergiant is a type of star that has expanded to enormous proportions after exhausting much of its hydrogen fuel, glowing with a deep reddish colour. UY Scuti is also a pulsating variable star, which means its brightness changes over time. At its brightest, it reaches a magnitude of 8.29, and at its dimmest, it falls to magnitude 10.56, far too faint to be seen with the naked eye. This star is considered one of the largest known in the universe. Its radius is estimated at 909 times the radius of the Sun, which translates to about 632 million kilometers, or roughly 4.23 astronomical units. To put this in perspective, if UY Scuti were placed at the center of our solar system, its surface would extend beyond the orbit of Mars and possibly reach into the asteroid belt. Its volume is staggeringly large, about 750 million times that of our Sun, making it a true giant in every sense. UY Scuti was first catalogued in the year 1860 by German astronomers working at the Bonn Observatory. These astronomers were completing a detailed survey of the stars known as the Bonner Durchmusterung Stellar Catalogue. In this catalogue, UY Scuti was listed as the 5,055th star, located between 12 and 13 degrees south, counting from 0 hours of right ascension. When astronomers observed the star again in a later survey, they noticed slight changes in its brightness, indicating that it was not a constant star but a variable one. Following the international naming system for variable stars, it was given the designation UY Scuti, marking it as the 38th variable star discovered within the Scutum constellation. In terms of location, UY Scuti lies a few degrees north of the A-type star Gamma Scuti and northeast of the famous Eagle Nebula. Despite being incredibly luminous, the star appears relatively faint to observers on Earth, only reaching a 9th magnitude at its brightest. This is largely due to its vast distance and its position within a dense region of the Milky Way called the Zone of Avoidance, part of the Cygnus Rift, where interstellar dust blocks much of its light. UY Scuti is enveloped in a thick shroud of dust, which contributes to its brilliant red appearance. It is classified as a semi-regular variable star, with a pulsation cycle lasting approximately 740 days. Earlier measurements of its radius suggested an even larger size of 1,708 solar radii, which would have implications for how its pulsations relate to its internal structure. In the middle of the year 2012, astronomers used amber interferometry on the Very Large Telescope in Chile's Atacama Desert to measure several red supergiants near the center of our galaxy, including UY Scuti, AH Scorpii, and KW Sagittarius. All three stars were found to be over 1,000 times larger than the Sun, and over 100,000 times more luminous. Among them, UY Scuti stood out as both the largest and most luminous. Its radius at that time was calculated at 1,708 solar radii, which is over 1,188,000,000 kilometers, or nearly 8 astronomical units. Its luminosity, or total energy output, was estimated at 340,000 times that of the Sun, with an effective surface temperature of 3,365 Kelvin. Its initial mass was thought to be around 25 solar masses, potentially reaching 40 if it were not rotating. More recent studies in the year 2023 using advanced monitoring techniques that track multiple signals from supernovae suggested a somewhat smaller radius of 909 solar radii, a luminosity of 124,000 suns, and a slightly hotter surface temperature of 3,550 Kelvin. Measurements from the Gaia Space Observatory suggest a parallax of 0.6433 milliseconds, implying a distance of roughly 1,500 parsecs, or about 4,900 light-years. This would suggest smaller luminosity and radius values around 86,300 to 87,100 suns and 755 solar radii. However, the Gaia measurements may be unreliable due to interference in the data. The most reliable modern estimate, based on data from 2021, places Scuti at around 1,800 parsecs, or 5,900 light-years away. Scuti does not have any known companion stars, leaving its exact mass uncertain. Theoretical models suggest its mass is likely between 7 and 10 solar masses. The star is also losing material at a rate of about 5.8 times 10 to the -5 solar masses per year, creating a complex environment of gas and dust around it. According to current models of stellar evolution, Scuti is already fusing helium in its core, while still burning hydrogen in a surrounding shell. Its position deep within the Milky Way disk indicates that it is rich in heavier elements. Eventually the star will produce iron in its core, upsetting the delicate balance of forces that hold it up. This will trigger a catastrophic collapse of the core, leading to a supernova explosion. Before this dramatic end, Scuti is expected to evolve into a hotter type of star, potentially becoming a yellow hypergiant, a luminous blue variable, or a Wolf-Rayet star, shedding massive amounts of material through powerful stellar winds. Ultimately, it will explode as a type IIb, or type IBX supernova, leaving behind either a neutron star or a black hole. At the very centre of our Milky Way galaxy lies a truly extraordinary and hidden giant, a supermassive black hole known as Sagittarius A star. This strange and mysterious object cannot be seen with human eyes, yet its powerful presence controls the heart of our galaxy. When viewed from Earth, Sagittarius A star appears close to the boundary between the constellations of Sagittarius and Scorpius, only a few degrees south of the ecliptic. It also lies near the sparkling butterfly cluster and the bright star Lambda Scorpii. Even though no visible light escapes from it, this black hole shines brilliantly in the form of radio waves, which astronomers are able to detect with powerful instruments. A great milestone in astronomy came on the 12th day of May in the year 2022, when the Event Horizon Telescope collaboration released the very first image of Sagittarius A star. This breathtaking image was created using data that had been gathered 5 years earlier, in 2017. It was proof beyond doubt that a supermassive black hole hides at the core of our galaxy. This became only the second direct photograph of a black hole ever taken in human history, a triumph that required half a decade of careful calculations and analysis. To achieve this, scientists combined signals from 8 radio observatories spread across 6 different locations around the world. By using a clever method called aperture synthesis, they created detailed images of the black hole's radio emissions, even though the task was very difficult, because these emissions change within just minutes. From these efforts, astronomers found that Sagittarius A star appears to have an angular size of about 51.8 microarc seconds, with a margin of error of plus or minus 2.3 microarc seconds. Because it lies about 26,000 light-years away from Earth, this tiny angle translates into a true diameter of roughly 51,800,000 kilometers, which is about 32,200,000 miles. To give a sense of scale, Earth orbits the Sun at a distance of about 150 million kilometers, while the planet Mercury at its closest approach comes within about 46 million kilometers of the Sun. Sagittarius A star also drifts slightly through space, moving about negative 2.7 milliarcseconds per year in right ascension, and negative 5.6 milliarcseconds per year in declination. Careful study of its gravity has provided one of the sharpest tests of Einstein's general theory of relativity, and every result so far has matched his predictions perfectly. In 2019, further discoveries were made with the help of NASA's SOFIA aircraft, which carried a special instrument called the High-Resolution Airborne Wideband Camera Plus. These observations reveal that magnetic fields play a major role around the black hole. They twist and shape the glowing ring of gas and dust surrounding Sagittarius A star, where temperatures range from almost minus 280 degrees Fahrenheit to more than 17,500 degrees Fahrenheit. That is, from about minus 173 degrees Celsius to nearly 10,000 degrees Celsius. These magnetic fields guide matter into orbit around the black hole and keep its energy output surprisingly calm, given its immense power. We cannot see Sagittarius A star in ordinary light because the path to it is blocked by clouds of gas and dust. These clouds scatter and absorb almost all the visible light, dimming it by about 25 magnitudes. The first clue to its existence came in April of 1933, when Karl Jansky, a pioneer of radio astronomy, detected mysterious radio signals from the direction of Sagittarius, the region of the galactic centre. Later, Jack Piddington and Harry Minnitt in Sydney discovered a strong and compact radio source in the same area. As larger and more advanced telescopes were built, astronomers confirmed that this radio source marked the very heart of the Milky Way. More detailed studies showed that the region called Sagittarius A was not a single object, but a cluster of overlapping sources. The brightest and most concentrated part, which we now call Sagittarius A star, was first identified in mid-February of 1974 by Bruce Ballack and Robert L. Brown at the National Radio Astronomy Observatory. In 1980, Brown gave it the name A star, inspired by the way atoms have excited states, marked with an asterisk. By the 1980s, strong evidence suggested that Sagittarius A star must be a black hole. In 1994, a group of researchers from Berkeley, including Charles H. Townes, a Nobel Prize winner, and Reinhard Genzel, who would later win the Nobel Prize, used advanced infrared and sub-millimeter techniques to estimate that its mass was around 3 million times the mass of our Sun. A dramatic leap in understanding came in mid-October of 2002, when Reinhard Genzel and an international team tracked the movement of a nearby star called S2 over a period of 10 years. The star's orbit revealed that the central object could not be a cluster of ordinary stars or exotic compact remnants. It had to be a supermassive black hole. These observations, made in near-infrared light where dust causes less interference, showed that Sagittarius A star holds about 4,100,000 times the mass of the Sun, all crammed into a space no larger than 17 light-hours across. For comparison, its Schwarzschild radius, the ultimate point of no return, measures only about 12 million kilometers, or 0.08 astronomical units. Knowing the distance to the galactic center is vital for cosmic measurements, and astronomers have placed it at about 8,000 parsecs, or roughly 30,000 light-years. In November of 2004, researchers discovered a possible intermediate mass black hole, about 1,300 times the mass of the Sun, located only 3 light-years from Sagittarius A star inside a cluster of 7 stars. This discovery may reveal how supermassive black holes grow, by swallowing smaller black holes and nearby stars. After 16 years of observing stars orbiting Sagittarius A star, a team led by Stephen Gillison calculated its mass to be about 4,300,000 solar masses. Their results, published in 2009, provided some of the strongest evidence yet that supermassive black holes are real. Genzel himself declared that the motions of the stars were proof beyond any reasonable doubt. Although often quiet, Sagittarius A star sometimes shows bursts of activity. On the 5th day of January in 2015, NASA detected an X-ray flare 400 times brighter than usual, likely caused by an asteroid being torn apart, or by magnetic fields twisting within the inflowing gas. On the 13th day of May in 2019, astronomers observed another flare, this one 75 times brighter than normal, perhaps due to a passing object falling into the black hole. And as recently as June of 2023, scientists detected mysterious radio filaments surrounding Sagittarius A star, deepening the mystery of this galactic heart. Another key discovery came on the 31st day of October in 2018, when astronomers confirmed with certainty that Sagittarius A star is a supermassive black hole. Using the gravity interferometer in combination with the 4 huge telescopes of the Very Large Telescope in Chile, scientists created a virtual telescope as wide as 130 meters, or nearly 430 feet. This enormous virtual lens allowed them to see clumps of gas whirling around the black hole at speeds of nearly 30% of the speed of light, a breathtaking confirmation of the incredible power hidden at the center of our galaxy. In addition, astronomers saw 3 very bright flares caused by highly energetic electrons moving dangerously close to the black hole. These flares acted exactly as scientists' models had predicted, showing the paths of hotspots orbiting a black hole with a mass of about 4 million suns. Scientists think these bright bursts come from strong magnetic interactions in the hot gas spinning near Sagittarius A star, giving a clear view of a cosmic storm far beyond what we can see directly. Earlier that year, in July of 2018, another amazing observation was reported. A star called S2, orbiting Sagittarius A star, was recorded moving at an incredible 7,650 kilometers per second, about 17.1 million miles per hour, which is roughly 2.5% of the speed of light. This measurement happened when the star was at its closest point to the black hole, called the pericenter, in May of the same year. At that time, S2 was about 120 astronomical units away, which is about 18 billion kilometers, or 11 billion miles, roughly 1,400 times the Schwarzschild radius of the black hole. At such a close distance, Einstein's theory of general relativity predicted that the star's light would be noticeably stretched by gravity, adding to the usual stretching caused by its fast movement. Remarkably, this effect was seen and matched Einstein's predictions within 10%, giving another strong proof of relativity in action. Interestingly, the radio waves coming from Sagittarius A star do not come directly from the black hole itself. Instead, they come from a bright area around it, near the edge of the black hole. This could be part of the spinning disk of matter, or a fast stream of material being ejected from it. If the radio waves came perfectly from the black hole, gravity would bend the light and create a ring-like shape. According to general relativity, this ring would be about 5.2 times the Schwarzschild radius of the black hole, or around 52 microarc seconds. Observations show that Sagittarius A star looks almost this size, about 50 microarc seconds, while the black hole itself appears to be about 20 microarc seconds across. Lower resolution images show that the radio source around Sagittarius A star is balanced and even. Some other theories of gravity could make images that are hard to tell, apart from those predicted by general relativity, but computer models show that the even look and small size match what we expect from a black hole, confirming that Sagittarius A star is indeed a supermassive black hole. Scientists have measured the mass of Sagittarius A star using many methods. 2 groups, one in Germany and one in the United States, carefully followed the orbits of stars close to the black hole. Using Kepler's laws, they estimated the mass inside these orbits. The German team calculated about 4.31 million suns, with a margin of error of plus or minus 380,000 suns. The American team found a similar number, about 4.1 million suns, with an uncertainty of plus or minus 600,000 suns. Since this mass is packed into a sphere only 44 million kilometers across, it makes a density 10 times higher than earlier estimates. Later studies looked at thousands of stars within roughly 1 parsec, just over 3 light years, of the black hole. Using statistics, astronomers estimated the black hole's mass at about 3.6 million suns, plus 200,000 and minus 400,000 suns, with another 1 million suns spread in the same area. This extra mass likely comes from normal stars and remnants of dead stars. Even though it is huge, Sagittarius A star is relatively small for a supermassive black hole, and its faint radio and infrared signals show that the Milky Way is not an active Seyfert galaxy. Importantly, what we see is not the black hole itself. It is still invisible, but the glowing gas and dust heated to millions of degrees as they spiral inward. The black hole itself only gives off an almost unimaginably faint Hawking radiation, around 10 to the minus 14 Kelvin, far too faint to detect. More proof comes from high-energy observations. The European Space Agency's gamma-ray observatory, Integral, detected gamma rays hitting the nearby giant cloud Sagittarius B2, which made X-ray light from the cloud. The total brightness from this event was estimated at about 1.5 times 10 to the 39th ergs per second, 1,000,000 times brighter than Sagittarius A star now, and similar to a typical active galactic nucleus. In 2011, Japanese astronomers using the Suzuki satellite confirmed these results, strengthening the evidence of the black hole's influence. In July of 2019, astronomers reported a star called S5 HVS1, moving through space at an amazing 1,755 kilometers per second, or nearly 4 million miles per hour, about 6,000ths the speed of light. This star in the southern constellation Grus, or the Crane, about 29,000 light-years from Earth, may have been thrown out of the Milky Way after a close encounter with Sagittarius A star, showing the black hole's huge gravitational power. At the centre of our Milky Way galaxy is Sagittarius A, a supermassive black hole full of mysteries. Orbiting very close to it is a group of stars called the S-stars. These stars are extraordinary. They move in dizzying paths around the black hole, tracing the invisible pull of a force so strong it bends space and time. Because clouds of cosmic dust block visible light, astronomers study these stars using infrared light, especially in the K-band, which can pass through the dust. The study of the S-stars is changing quickly. In 2011, astronomers mapped the orbits of the main stars at that time, comparing their loops around Sagittarius A to the planets in our solar system. There was excitement when a 62 seemed to swing closer to the black hole than any other star seen before. Later, observations showed that this approach was not as extreme as first thought. The S-stars are valuable because of their speed and closeness to the black hole. This helps scientists measure the size of Sagittarius A and see subtle effects predicted by Einstein's relativity, like the shift of a star's closest point in its orbit. Researchers also watch for stars that might get too close and be torn apart, but fortunately, none are expected to meet that fate. As of 2020, the closest approach record is held by S4714. This star gets to about 12.6 astronomical units, about 1,880,000,000 kilometers, of Sagittarius A. This is nearly the same distance as Saturn from the Sun. S4714 moves at almost 8% of the speed of light. Its orbit takes about 12 years, and it is very elongated, with an eccentricity of 0.985, explaining its close approach and high speed. These numbers have uncertainties. The closest distance could vary by plus or minus 9.3 astronomical units, and its speed by plus or minus 8,840 kilometers per second. Detailed tables exist for the S-star cluster, listing each star, its orbital size and shape, tilt and direction, closest approach times, infrared brightness, and speed and distance at the nearest point to Sagittarius A. One interesting visitor is the gas cloud G2. First seen in 2002, G2 has a mass about 3 times Earth's. In 2012, a paper suggested that G2 was on a path toward the black hole's accretion zone, the area where matter spirals inward and disappears beyond the event horizon. Predictions said G2 would reach its closest point, or perinigricon, in early 2014, at just over 3,000 times the black hole's radius, around 260 astronomical units, or about 36 light-hours away. Observations since 2009 showed the cloud slowly being pulled apart. Some scientists expected it might be destroyed, creating bright X-rays and other light. Others thought G2 could hide a dim star or be 2 stars merged together, keeping it intact near the black hole. In May of 2013, scientists suggested that before the closest approach, G2 might have close encounters with other stars or remnants like neutron stars orbiting the black hole. Studying this could give a rare look at the extreme area around Sagittarius A. Astronomers were eager to watch G2 because the black hole usually eats matter very slowly for its size. Being so close lets us see even faint activity, and G2's path offered a natural experiment to learn more about how supermassive black holes feed. Many observatories focused on the event, including Chandra, XMM Newton, the Very Large Array, Integral, Swift, Fermi, and requests were made for the Very Large Telescope and Keck Observatory. Teams at the European Southern Observatory and Lawrence Livermore National Laboratory simulated the cloud's journey. Astronomer Darrell Haggard said, "It's exciting to have something that feels more like an experiment, hoping the event would show new insights about black holes." When the closest approach happened in March of 2014, the event was underwhelming. No spectacular fireworks appeared. Observations on the 19th and 20th of March confirmed G2 was still intact, meaning a star at its centre likely kept it together. Further studies on the 21st of July 2014, using the Very Large Telescope in Chile, suggested that G2 might not be a simple cloud at all. Instead, it could be a dense clump in a larger, thinner stream of gas, slowly affecting the black hole's accretion disk rather than causing sudden bright bursts. This idea gained support from observations of a similar cloud, G1, which passed near the black hole 13 years earlier and followed almost the same orbit. Together, these clouds, along with a trailing gas tail, appear to be part of a continuous stream of matter. Astronomers, including the renowned Andrea Ghez, suggested that G2 might not be just a simple cloud of gas, as many had originally thought. Instead, it could be the result of a dramatic cosmic event. Two stars that once orbited each other as a binary pair might have collided and merged to form a single, much larger star. This bold idea helps explain a puzzling observation. Despite being so close to the supermassive black hole at the centre of our galaxy, G2 managed to survive without being torn apart by the black hole's overwhelming tidal forces. The S-stars, along with passing objects like G2, are far more than mere points of light or curiosities drifting through space. They act as living laboratories on the edge of one of the most extreme and dangerous regions in the Milky Way. By studying them, astronomers have rare and invaluable chances to watch the fundamental laws of physics in action, revealing how matter behaves when confronted with one of the universe's most mysterious and powerful forces.